To welcome Professor Nils Anderson with us. As you know from the schedule, he's down to lecture for several hours today. Nils is Professor of Applied Mathematics at the University of Southampton, and he leads one of the largest groups in Europe working on gravitational physics. He's an expert in Einstein's theory of general relativity and related astrophysics, has done seminal theoretical work on many extremes of physics involving black holes, neutron stars, and gravitational waves. His current research is particularly focused on neutron star phenomenology and the underlying nuclear physics and complex fluid dynamics. Nils has held several prestigious fellowships, including the Leverhulme Prize Fellowship in Astrophysics, and is an elected Fellow of the Institute of Physics. As those of you who know Nils, and I know a few of you do, you'll know that he's a keen science communicator, has given frequent popular talks on matters of gravity, including at the Science Centre in Valencia and the Museum of London. He's written a series of science-related books for children, including A Gentle Wizard, which provides an entertaining and personal introduction to Einstein's universe. Nils, with that, over to you. Welcome.
Thank you. Thanks to you. Read that very well. I remember writing it. Good morning. If I seem a little bit confused at some point and lose the plot or something, it's because I've just come back from India, where I lectured last week at another summer school. Their schedule for me was a little bit tougher than this week, although today will feel a bit similar. I had 3 hours a day for 5 days, culminating in a public talk on Friday, after which it was everything went kind of crazy. What I thought was I'm going to change the strategy a little bit from what I expected, although I wasn't here last week, so I really don't know what people talked about, right? But I decided to set the target in a slightly different place. I assumed that last week you would have talked a lot about black holes, just looking at the speakers and, et cetera, et cetera. So I thought I wouldn't talk about that at all. And then I thought that the brief gravitational wave sources was way too big for me to deal with, okay? So I decided to split this up into 3 pieces. In the first lecture, I'm going to talk a little bit around how you put matter into the problem. And I'm going to try to connect with the equation of state for neutron stars, what physics goes in and how we put it in. That's my main target for this first lecture. The second lecture, I'm going to talk about something I suspect Satya might have talked about, namely rotating stars. Did he do that at all? Okay, he did the quadrupole formula, that's good. So I'm going to sketch that again, but just remind you. I'm going to talk to you about why that problem is much harder than you might think if you just look at it from the sort of textbook point of view, which might be a bit disappointing. Maybe all of my lectures will be disappointing. I'm used to that, so that's okay. And then in the third lecture after lunch, I'm going to look at what I'm going to call anatomy of a merger. And I'm going to go through 3 aspects of neutron star mergers. And basically what I'm hoping to get to is to close this loop with this first lecture, basically talk about how we hope to extract information about the matter inside neutron stars from mergers in particular. Okay? So I've confined myself essentially aiming to that point. Okay? So I'm going to talk a little bit about numerical relativity, which I think Mark probably went into some detail about. I'm not going to talk about anything about actual simulations. I'm just going to talk about, again, what happens if you do numerical relativity and you want to deal with matter. And the point I want to make there is that it's not easy. So that's where I'm going. I have a dying laptop. There you go. I have put everything on slides. There was a simple reason for that. I wanted to avoid confusion. Okay. So as I said last week, I gave 5 90-minute lectures. They were all on the blackboard. So I thought if I do these ones on slides, I can at least keep clear in my mind what is what, right? Otherwise, I could just end up giving you these 5 90-minute lectures in 3 hours, and that might not be the best idea on the planet, okay? And so that's why I did it like this. Okay, so I'm going to start by recapping. But the problem we really want to solve, obviously, is this one. So the Einstein field equations. And if my suspicion is right, you talk quite a lot about how you deal with this side. And you talked a little bit about how you deal with the matter content, probably in terms of the mass quadrupole, where essentially what you do is you think of the solution to the Einstein field equations in some sense perturbatively. So you have some background space-time. In the simple context, it's flat. You have something on the right-hand side that generates waves, knowing that the left-hand side is going to give you some wave equation. We'll show that in a sec, just to remind you, because it's Monday morning. We need to be reminded of sort of the very basics of existence, I think, to get going, okay? And then you have to keep in mind that what sits over here is not the full matter stress energy tensor, but only the piece that gives you the waves on the left, okay? So much of my focus is going to be on this guy. What do we put in here? How do we deal with it? Okay? Another way of looking at the same kind of question is a bit like this. So here's an image I've stolen from Jocelyn Reed and fiddled about with it a bit to make it. There are different ways of solving gravitational wave modeling problems. Okay? You've talked about the post-Newtonian expansion, I'm sure, last week, the leading term of which is the quadrupole formula, and then you go to higher and higher orders and the equations get messier and messier, and at some point, you, like me, you probably stop paying attention. I don't know, there's probably some rule for the human mind as to what the longest equation you can actually look at and make sense of, and I think the guys that do post-Newtonian expansions have beaten that many times over. In fact, it ended up being kind of a metaphysical discussion with Bal Ayer, who's an expert in that field. And I was trying to get, so you know, they've calculated the radiation reaction to 3.5 pn order. The equation is about this long with the smallest type font you can find. And I tried to ask him, given that he's about to retire, or has just retired kind of, if he's going to go for the next order or not. And he just gave me this look, and then we started talking about how long an equation you can take in before it's just too much. And for me, it's about one line, a short line. And then I just start going a bit fuzzy. All right, so the idea is something like this, that you heard about post-neutron. So if we take a neutron star binary in spiral as our target, we would start off doing post-Newtonian point particle in spiral somewhere way before we enter the LIGO band. Entering the LIGO band, at some point, we need to switch to fluid perturbation theory, where we think of the stars as being maybe non-rotating, whatever, equilibrium stars with some perturbation, because as the stars get closer and closer together, the tidal interaction is going to stretch them, and so they're not point particles anymore. Basically, the finite size of the neutron stars come into play. So we think that happens at something like a few hundred hertz maybe. And then there's no discussion when you get to the actual crashing together of these stars. It's not post-Newtonian theory anymore. It's full-blown numerical simulations. It's the only way to do this problem. Okay? So one way to do it, this is pretty much mapping out my 3 lectures, although these 2 are probably in the 3rd one. Okay? So we talk about post-Newtonian, how we do put things into the quadrupole formula, and then I'm going to try to get all the way to here, but I'm not going to talk about numerical relativity so much as a little bit about the ingredients, and then basically just look at some results to tie it all together. That's what I'm going to try to do. Okay? So here's a recap of something I suspect you've seen quite a lot of last week. So how does this go? Well, in a post-Newtonian sense, you start off thinking, well, I want to start off proving that there are waves. So you do an expansion saying flat space-time plus something else, ignore everything that's quadratic. Easy. Because you're doing this kind of calculation, you know that this guy has to still be quadratic, so you end up having this nasty minus sign if you look at the contravariant metric. And so this is a warning for everybody that's ever done any kind of calculations. Whenever there's a minus sign, you will go wrong. It's kind of a natural rule. I'll tell you a little bit later. No, I'll tell you now. So last week I made the mistake, okay, of asking the students to work out the size of, or the amount of deformation in the neutron star that I'm going to come to later. So how much you can stretch it, how much you need to stretch it to balance accretion from a companion. Okay? I thought this is a good exercise for the students to do, and then I made the foolish step of asking them to put in real numbers. So they had to put in numbers for like Newton's constant, you know, speed of light, mass of the star, radius, whatever, accretion rate, all sorts of numbers, okay? Now, when the first student put the hand up at some point, and I said, so what's the question? Is this right? He said to me. He had a deformation of the star, which Satya probably talked about, of 10 to the 20. Okay? So I tried to explain to him that if you take a star and you stretch it by an ellipticity of 10 to the 20, it's not a star, it's a line. And so he thought about that for a bit. He said, oh yes, I see what you're saying. And then I thought, okay, that was a bit bad. And then 5 minutes later or so, another person put their hand up, and they had 10 to the minus 20. So I thought, that's quite small. And then we kept on going. At the end, I sort of tried to get a census in the room as to how many people actually got the same answer. I had about 60 students, okay? I don't think there were 2 answers that were the same in the room. So we learned something about putting in numbers and signs. And in a way, it was kind of a very interesting exercise because I didn't, you know, I hadn't thought it through. Typical. Okay, I shouldn't say things like that while I'm being recorded, but okay. But I think, for me, I learned that don't ask students this kind of thing, because I'm not asking you anything. Okay? And secondly, if you do ask students this, try to turn it to your advantage. So what I did was I said, look, we've all learned that putting numbers into these equations is not easy. So at least there was some kind of lesson. Okay? And then they all got frustrated because I didn't tell them what the true answer was, because of course I knew if I put numbers in, all bets would be off. Okay? So I didn't do that. Okay? Anyway, so we calculate away. You know that what we do actually is we put this funny combination called trace reversed perturbation, where we just take this h and subtract off this piece, which just means that the trace, where you sum over the indices, is reversed. So why this combination? Well, the answer is very, very simple. We use this combination because this is exactly the combination in the Ricci here. Okay? You just replace this with an h, and this is exactly this combination. So this symmetry goes all the way through the calculation and comes back here. Okay? That's why the equations simplify a lot if you use this combination. And then, so that's the trace reversal, and that's basically it. And you work for a bit. You've probably all done this in some shape or form, and you show that yes, there is a wave equation, but you have to be sneaky and set this divergence of that trace reverse perturbation to 0. So what does that mean? Well, what is it? It's 4 equations because we have one free index. So what we're doing, in essence, is we're choosing coordinates. You know, in general relativity, we've got the freedom to choose whatever coordinates we like, and this is a statement of what coordinates you're using in a kind of odd kind of fashion. Okay? And then at the end of the day, that just crank everything through. It doesn't matter. You end up with the wave equation here. For that, where this is just the usual flat space wave operator. So it's minus d by dt squared plus all the essentially Laplacian in space. And then on the right-hand side, I've still kept it as t, but that's a cheat. What's sitting here is now only the stuff that gives you waves. So it's only the stuff that's asymmetric. Okay? And so, as an example of why we need to pay attention to that statement, let me tell you that again, when we talk about deformed stars later, I'm going to basically carry out an example calculation that shows that if I stretch a neutron star as much as I'm allowed by nature, not to the line, okay, but as much as I'm actually allowed, then that's not very much. In fact, it's so little that the centrifugal deformation that exists because the star rotates is much, much bigger, typically. And now here's a typical mistake that quite a few people, unfortunately, have made in the past. And it's one of these things that keep on coming back for some reason I don't quite understand. People have taken the centrifugal deformation due to the rotation as being the piece that gives you gravitational waves. Okay? But that's much, much bigger than the real deformation. And the problem is that this centrifugal deformation is symmetric, so it gives you no waves ever. And it leads to people making spectacular errors, again, in their actual quantitative calculations. Okay? So we need to figure out exactly what that is. So what you can do is just, now this is the usual flat space wave equation. So you use the flat space tools from undergraduate mathematics, if you like, or something like that, on PDEs. So you use retarded Green's function for the wave equation, integrate the wave, remove the trace and so on, project off, so you get the transverse piece. I'm sure Satya would have talked about all of this. So you get an H now with just space indices with some number, and this number is a very, very small number because Newton's constant is small, speed of light is large. You take the latter to the fourth power, so you're dividing the small with something very, very large. So this is an incredibly tiny number. So essentially all the challenges of gravitational wave physics are in this number, in this factor. They tell you why the waves interact so weakly with matter, and it tells you how nasty is everything. Why is it that we will never see anything to do with matter? Because this number is too small. And then you have the reduced quadrupole moment, and so on. And this, I suspect, is what Satya talked about, and I expect, although I don't know for sure, but you can tell me, that he looked at the luminosity and then probably gave you some idea of how you can estimate how big this number is. Is that right? So that's what I thought he would do. So, but the key point here is, again, a very, very common mistake that people have made, if you go to the literature and just see, when people estimate how important is some process that you invent, if you're a theorist like me, to generate gravitational waves, how important is it? Well, you can look at this kind of thing, and what people typically do in physics is they say, okay, I'm going from an initial state to a final state. Okay? The initial state has this much energy, the final state has got this much energy, say gravitational potential or binding energy, whatever you like. I take the difference between the two, and that clearly tells me how much energy is released. Right? So they do that, and they say, look, this is a way of getting an enormous amount of gravitational wave energy. You take, for example, a star, normal star, that collapses in a core collapse supernova. Right? And you ask, how much energy is released in this sort of collapse situation? And say, look, I can get a whopping large amount of energy out as gravitational waves. The problem with that kind of thing is you're forgetting these time derivatives. So in gravitational wave astrophysics, we're not interested in the final destination. We're interested in how we get there. It's the route to that final destination that matters. Okay? So taking a simple difference is not good enough. Okay? We need to know, how did the system go from A to B? How asymmetric is it? So in the case of core collapse supernovae, if you know a little bit about the history of this subject, in the 1960s, 70s, it was thought that supernova explosions were going to be a really good source for gravitational waves. Because in principle, the energy budget says you can release a lot of energy. Okay? As people started doing actual simulations, it was clear that this number was not so good compared. Instead of something like a tenth of the solar mass being released or something like that, the numbers went down. They were 1,000, and then there was suddenly 100,000 of the solar mass, and then they started putting in higher, multi-dimensional simulations. Latest 3D simulations say this number is maybe 1 part in 10 to the 8. So the number keeps on going down, and the lesson here is, again, something that's quite typical for gravitational wave modeling, kind of depressing in a way. It should never be depressing on a Monday morning. But on the other hand, maybe it's good to start the week in a sort of negative way, and then we can build up towards the end. You know, when my job is done, you know, someone can come in and be more upbeat, whatever. Okay? What we're learning in general, I think, is that as we understand problems better and put in more realism, right? The answers are never as good as when we just did back of the envelope sort of sketches, okay? The devil is in the detail, and it tends to be depressing, okay? That's not saying we shouldn't do it. We just have to keep on doing things better in order to understand how things actually go, okay? So there's some sort of general, fairly important lessons, I think, to set the stage for what we're going to do. So I'm going to talk about neutron stars. In principle, gravitational wave astronomy will not be astronomy until we deal with stars. Simply the word astro, right? Black holes are not stars. Maybe in some reductionist sense. They used to be, but they're not anymore. And so my argument is going to be, we will never do gravitational wave astronomy until we see neutron stars or white dwarfs. Right? That's going to be my revenge on the people from last week. Okay? Or maybe my reason for existing or something like that. Okay? So the point here is that neutron stars are exciting because they contain a lot of physics. I'm going to try to give you a flavor for what the physics is in a sec. And we think, or at least people have argued over the last decades, that there are a number of processes involving neutron stars that could be interesting. Okay? And they range from the obvious neutron star mergers, which I will get to, the core collapse that I just talked about when the neutron star is born, the deformations, which I will talk about in the next lecture, oscillations, etc., which I will only skirt around the edges of. It's quite a big area with its own problems, and I've decided for these 3 hours to leave most of that out, which might be surprising to some of the people that asked me to do this, but anyway, that's what I've done. So the lesson is a little bit like this. You can make this list. It's much longer than this. Each of these mechanisms is easy to understand. In the back of the envelope, kind of just saying this is how it goes. To actually work something out and model in some kind of realism is really hard. Okay? And so there's a completely different level here. And that means that when you talk to people about, are we ever going to do this? So if you talk to someone that doesn't work on neutron star modeling, but on gravitational wave searches, for example, they're going to say, of course we are, it's only a matter of time. Okay? And then you ask someone like me that tries to work on these problems every day, and I'm going to say, it's never going to happen. Okay? And that's not because I'm a pessimist in any shape or form. In fact, in order to work on a problem where you think this is going to be really hard, you have to be the ultimate optimist, right? You have to have a reason to get up in the morning, and you know the answer is going to be hard, and getting there is going to be difficult. Okay? So what I'm going to try to do, essentially in all these lectures, is explore why is this so hard, and by taking that attitude, what I'm trying to achieve is sort of give you a flavor of, yes, this is very hard, but the reward for doing it could be exceptional. Okay? But I'm not going to take the view of saying, oh, it's not a salesman's talk. I'm going to say, look, this is going to be fantastically good. I'm going to say this is going to be really hard, but if we get there, it could be, well, moderately good. Okay, so here's my picture that I made of a neutron star. And I'm going to use this to explain why this is hard. Okay? So a neutron star, as you know, is a dead star born in the supernova core collapse. It is something like 10 kilometers in radius, 1.5 times the solar mass. Okay? So what happens if you cram that sort of mass into 10 kilometers is you get all sorts of funky physics that we're not used to. Things we can't test in the laboratory. not even with the collisions at CERN. And so from the theory point of view, one reason for working on neutron stars is you get to play with all of physics. Okay? And that's kind of good. Kind of confusing, but kind of good. Okay? So we need gravity. Why? Well, we want to talk about gravitational waves, so we need some gravity. Also, we need something to hold the star together. We need electromagnetism because we know we see radio pulsars, we see magnetars, we see them because they have magnetic fields, right? But also we need to understand what this magnetic field can do for us as gravitational wave astronomers. We'll come to that in the second lecture a little bit. We need the strong interaction, so we need particle physics. Maybe that's why, in a sense, gravitational wave physics is part of astroparticle physics in a wider sense. There's a strong connection here. We need a strong interaction because the strong interaction tells us what the star is made of, what is the composition at these extreme densities. And we need the weak interaction, the one that involves neutrinos, because it's ultimately slow reactions that tell us how the star evolves. How does it cool? What are the different friction mechanisms if we try to let the fluid wobble about and so on. Okay? So we need to take all of these and stir. And it's a bit worse than that, because if we start asking what happens if I start at the surface, where essentially, simplistically, you've got iron, which is the most stable of all the atoms, and then we start marching towards higher densities. Well, we start off with an outer region that's essentially an iron lattice. Right? It's just an iron ball. It looks like an iron ball, but when we go a little bit deeper, keep on pushing, we get to neutron drip, where the neutrons decide to abandon the atoms. They want to form their own team. And so now we have that lattice, but we have a free neutron gas, which introduces another aspect, namely superfluidity. So this neutron gas can flow in some sense without friction through the other guy. Okay? We keep on going. At some point, the protons in the nuclei also want to have their own team. So they drip out of the nuclei. Essentially, the nuclei are unstable. And now we have a neutron, proton, electron gas, where, to make things complicated, even more complicated, the protons probably form a superconductor. Okay? So now we have something we're not used to at all. We've got a neutron superfluid living together with a proton superconductor. Okay, so not only do I have these guys, I also have low temperature physics. And you know, maybe in superconductivity, people are very proud of doing high temperature superconductors, where they manage to get some, what we would call probably quite low temperatures. These guys are sort of the ultimate high temperature superconductors, given that a neutron star is something like 10 million Kelvin. Right? So when your low temperature friends say that they're dealing with high temperatures, you just say, forget about it. Keep on marching on, and we get to the point where we really don't know what's going on, because we've got other kinds of particles, hyperons, kaon condensates, pion condensates, and so on. And at some points, even the quarks want to have their own team, so they start dripping out of the nuclei. We might have something like a quark-gluon plasma of the kind that people at CERN and RIC and so on, colliders, try to study. Okay? So basically, the bottom line here is, this is an immensely complicated object. Okay? And it's worth keeping this in mind when I start talking about how we model them, because you're going to see that I'm now going to, having described all this stuff, I'm now going to take a couple of steps towards sort of almost ultimate reductionism. Where I'm just going to say, actually, this looks quite hard, but I'm going to make it as simple as I can. Okay? Now, the problem with that is twofold. One is, I need to remember that I started off with a very complicated problem. Okay? And then I simplified it for my own purpose, because otherwise I can't deal with it. Okay? But it's important to keep that in mind. A lot of people that do gravitational wave modeling forget the origin of the problem, if you like, that there is a lot of physics from the beginning. Okay? And then they start believing things like, oh, actually, the matter content here is really quite simple. It is not. Okay? The devil really is hiding in this kind of diagram. And there's a lot of stuff to think about, a lot of questions, a lot of things we really, really don't understand. Okay? People don't like it when people like me say that sort of thing. They ask, how does it work? I say, I don't know. Ultimately, it's like people like you in the next many decades, or your children's children's children or something, that will solve it. So how does this work? Well, in reality, what happens is we put together something called the equation of state. The equation of state is a piece of magic that should encode all of this physics. Okay? Essentially, it says, what is the relation between these different quantities? The way it's typically written is some relation between pressure and energy density. We'll sketch this in a sec. And my aim now is to talk about what happens in a little bit more detail when we put matter into the equations of general relativity. And then I want to just get to the point, well, give you a flavor of how it's not quite as simple as we often pretend. That's all I want to do. Okay? I'm not trying to give you some working knowledge. I'm not going to challenge you by asking you to do anything for me, etc. But basically, we know that there is some relation for whatever the matter constituents are that should allow us to calculate, say, what is the mass of the star radius for a given central density, something like that. Okay? We know, dating back to the 1930s, essentially, that there will be a maximum mass any of these equations of state can sustain. So maybe we can use that as a discriminator and decide what equations of state are acceptable, which ones are not. We know what kind of physics we would like to put in. So the question is, can we stomach all of it? Okay. So where are we with this today? Well, I'm going to try to give you a sort of flash overview that takes about 2 minutes. Well, we know that in binary systems, we can weigh the individual stars. So we have some set of masses, but, you know, there's some range. We've gone, at least in the recent past, from thinking that all neutron stars have a mass between something like 1.3, 1.4 solar masses, up to knowing that some are more massive. So this is changing a little bit. We're trying to use X-rays associated with surface phenomena, say explosions on the surface that we see as X-ray bursts, to constrain how big the star is. I'm going to show you in a second roughly what the current state of play is, but we think we know that the radius should be something like 10 to 13 kilometers. So it's still quite a large error bar. Okay? Now we need to keep a few things in mind. For obvious reasons, if you try to calculate what this equation of state would be from first principles quantum physics, okay, this is hard. Okay? So this is beyond where we comfortably can go, even though some people are comfortable with more harder things, so they go in this direction. So I'm going to try to show you, I'm going to show you on the next slide, on the next 2 slides, what the current error bars on this kind of thing is, because that's useful to know. A key highlight, I think, which is nice for us, is that what we expect to be able to do with a bit of luck with future astrophysics experiments, not just gravitational waves, may be better than our colleagues in nuclear physics can do with their experiments. So, for example, in testing this equation of state, there is an experiment called PREX, which aims to measure for lead. Well, there was an experiment for lead, and they're repeating it to get better error bars, smaller error bars. How much the neutrons in lead stick out from the protons. So there's a little thin, very thin skin of neutrons sticking out of the lead nucleus, if you like. Okay, and that gives you some constraint on, funny enough, the equation of state for neutron star mass. So what's going to happen in terms of where we are and where we go? So we're going to talk about how we might be able to use the tidal interaction in neutron star binaries to constrain the size of neutron stars. I'm not sure, Chris Vandenbroek probably talked about that. Is that right? Okay. So I'm going to talk about that problem in the final lecture a little bit from the theory point of view. Now, we think maybe that's going to give us something like a 500-meter error bar on the neutron star radius at some distant point in the future when we've got many observations. Okay? So that's good. That would be fantastic, given that you can see I've got error bars here that's much bigger than that. But there is an experiment called NICER that's flying on the International Space Station right now that is expected to do that for one or two or a few neutron stars. Okay? So it could be that we will be a decade too late. We should be kind of disappointed. Of course, they could fail, but we should never wish our colleagues to fail, especially some of our colleagues, like in our group in Southampton, we've got a colleague that's involved in the NICER with that experiment. So I don't really want them to fail, although, you know, as a gravitational wave physicist, maybe I should. I don't know. Okay? The square kilometer array is going to see many, many more neutron stars. So we should see many, many more binaries, and therefore we'll get many, many more masses. So we're going to get a better census of these things. Radio astronomers will never see the radius, or may be able to measure the radius of a neutron star, but the masses, we're going to get a sort of census of that. Athena, other X-ray instruments will continue, hopefully, to see these surface phenomena. The only problem right now is we don't have an instrument to replace the Rossi X-ray Timing Explorer, which was the supreme instrument for finding out these kinds of things, because it could do precision timing. There's no such thing apart from the Indian AstroSat thing that's flying at the moment. And there is not clear yet how much data that's going to be sort of generally available. So that's why there's been several proposals here, including a thing I worked on, which is called LOFT. It was not funded by the European Space Agency. There is a thing called EXTP, which is a collaboration between ESA and China. That's in the pipeline. There is an American version of this LOFT that's being discussed. And these missions are incredibly important if you want to try to do this kind of thing with electromagnetic observations. Okay? And the timescale on which this will happen, we don't know. So let's see what we actually know in a sort of Donald Rumsfeld kind of things we know or we don't know. So here's my diagram. You probably can't read it, so I'm going to tell you what it has. It's got three different kinds of boxes for single neutron stars and binaries. It's got green things that we know. Okay? We know that the fastest neutron star spins a fair bit below the theoretical breakup limit at 716 Hertz, the current record holder, where the breakup limit is over a kilohertz. 716 Hertz, 716 rotations every second with 10-kilometer object weighing more than the sun. That's kind of impressive. F sharp, I think, 716 Hertz, if you care about the musical bits. We know that we can read off the masses. We know that the record holder is just a little bit heavier than twice as heavy as the sun. Okay? We know, as I'm sure you know, from double pulsars like the binary pulsar and so on, that we do have gravitational waves, also from neutron stars. Of course, this was where we first had indirect evidence that gravitational waves were real. So these are, and then we think we know at least, that the fast-spinning neutron stars are sort of reborn by consuming, like in a cannibalistic fashion, their partners. So they gain angular momentum as they accrete matter from a companion. And the fastest guy we know here spins at 640 Hertz. So that ties together with this fast one. And these four things, I think, are all the things we really know. We know. Then I got a sort of yellow light that says like in driving, we should not march on, we should stop and think a bit. So these are go slow kind of things. We infer the magnetic field of neutron stars from the spin down rate. Right? So we measure the spin down rate with radio astronomy, and then we say, well, if it is a rotating misaligned dipole magnetic field, the star should spin down like this. Okay? And then we say, oh, that tells us what the magnetic field strength is. Okay? But life is not quite that simple. So this is an estimate. I think sometimes when we look at these numbers, we think this is the real answer, but we don't know for sure. So there's some unknown error bars here. When we connect this spin-up thing, we think, or usually, we assume a link between the mass accretion rate and the spin-up rate. Okay? And then we can do that, as I'll talk about later, to connect with what level of gravitational wave emission do we need to balance this. Okay? But there's an unknown factor here, some efficiency, say, that we really don't know. Okay? So if you go to the literature and look at these kinds of papers, I'm guilty of this, as guilty of this as anyone, there's a sort of a factor somewhere in there that people tend to say, yeah, it's probably 1. But that saying, it's probably 1 is just complete ignorance. Okay? And I think, if you look a bit closer, I think we can convince ourselves that that's probably not true, and so we don't know. And then we've got quite a lot of things we don't know. We don't know how the pulsar glitch phenomenon works, where radio pulsars spin down gradually, and then every now and then they have a hiccup, so they spin up a little bit and then relax. Okay? We don't exactly know how that works. We think it's got to do with superfluidity and vortices and blah, 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 but we don't actually know. We don't have any models that can calculate this, even though there are many models that cannot calculate it. Okay? And again, I'm guilty. We have ideas, so we have some limits from gravitational waves on deformations. I'll talk about that later. We have some estimates. We have things like magnetar flares, where strongly magnetized stars, neutron stars, seem to oscillate. We think we have some idea where these oscillations come from, but if you look at the details of the models, they actually don't predict anything. Okay? We have radius expansion bursts, which is essentially where there's some explosion on the star's surface, the star expands a little bit, we can figure out how big the star is from that, and that's where you get these 10 to 13 kilometers. But again, we have no models that actually does this proper. We've got cooling, where we see neutron star upper limits on temperatures, try to reconcile that with this physics inside. We can make some progress, but there's a lot of stuff missing. So I think what I wanted to do is this kind of image is just to say, we know a lot of stuff, right? But this is a bit like a jigsaw puzzle where you first of all don't know how many pieces there are. You know how many pieces you got, I did 1, 2, 3, 4, and then you know some pieces you may have and some others, and you'd like to put them all together, but we don't know exactly how it goes. Okay? So there's a long way to go with this. So here's a sort of mass radius diagram where you get some flavor for where we are. This is a record holder in mass. Here's that 10 to 13 kilometers. These are all equations of state from different people. So what we know for sure is that if you need to reach this point, say this guy here that doesn't quite make it, they can't be real. But if you know any nuclear physicists, you know they're clever people. Okay? And so they would just say, well, yeah, didn't quite make it with this one, but I tweaked this little coefficient here, and then suddenly it's easily done. Okay? So what we'd like to do is discriminate between all of these and find out which is the real equation of state for matter. Okay? And to do that, we really need not just to have a limit here, we need something here. So here's this very faint, but you might see this fan here, pink. Pink for we really don't know. But this is essentially, if you take the calculations people are able to do, that gives you a constraint down here somewhere. And then you allow for all the options, the whole range of possibilities. That gives you this fan. And so basically, if the equation of state doesn't go through this big range here, big area, then I think we can probably rule it out already. But you see, this is quite a big error bar. So the bottom line here is a 500-meter box somewhere here. If you know the mass, say somewhere here, 500 meters would be a lot of progress. Okay? That's why this nicer experiment is important. That's why this discussion of what can you do with neutron star binaries is important.
Before you go to the next slide, can you say something about the cardinality of p less than infinity regions? Like what are those?
Okay, so basically here, if you want, in reality, the matter description has to be according to relativity, right? You cannot have sound waves moving faster than the speed of light. There are some of the models, like the classic ones. This is one by the Akmal, Panduripanda, and Ravenhall kind of models. They have parts in the star that are actually not causal, where the sound moves faster than the speed of light, because they are non-relativistic quantum calculations. Okay? And so there is an issue for some of these equations of state. But in principle, you know you can't go here, you know you can't have infinite pressure, so that, and then you know that you will form black holes at some point. Right? So these cannot be matter descriptions. Okay? You can also draw a diagram down here saying what we know from rotation. If you take the fastest spinning neutron star, right, you have to be allowed to have stars spinning that fast, and that gives you another constraint down here. So you can constrain this a little bit, but the point is there's a huge range of possibilities. We really don't know. And there's an enormous range of proposals for what we should be using. Okay. So I'm going to very quickly, to sort of wrap up in a couple of slides, talk about relativistic fluids. So how do we do this? I'm going to go from the textbook kind of thing that you would have seen probably if you've taken a relativity course, where you just say, I know from the Einstein field equation where I started, that if you take the divergence of this Einstein tensor that sat on the left, then that's 0. So that means that whatever sits on the right, which is the matter, has to be divergence free. Okay? So that's 4 equations here, there's 1 index there, that have to be satisfied. So most people now take this as being the equations for the matter. Energy conservation, momentum conservation, 4 equations. Okay? Now, personally, I think that's a bit simplistic, but okay, let's roll with it for now. It's Monday morning after all. We don't want to make it life too messy, okay? So what you do is you then say, okay, what is this T? Well, what most people do here is they say, let's assume, that is a natural starting point, that matter is a perfect fluid. And the way you think about this now, as usual, is just you have some flow line, a box of matter here, and with some parameter proper time, a clock that flows along this guy, some tangent vector that you call u alpha, say, which is the full velocity, okay? And then you say, in this box, I've got a pressure P and some energy epsilon, energy density or something like that, and then you track this along this flow, okay? That's the problem, and all the equation of state stuff is hidden in this box. It says, what sits in the box? And so this is the very simplest version you can have. A perfect fluid has only pressure and energy density. Okay? So then you just put this in, these equations, crank things through. You find that some equation, let's not talk about it. I have a piece that is along this flow of the equation. Okay? That gives me energy conservation. And it's sitting here, it's a time derivative along the flow. So this is a u contracted with derivative. So this is how the energy changes. And then another piece where this is the expansion, contraction of that fluid element. Right? So basically it says the energy changes if I expand and contract along this flow. If you're thinking of several of these guys, if they start diverging, you change the energy. Okay? So this is the usual equation. Now for our purposes, I want to do a little bit more. I want to think about what goes in here, okay? And unfortunately for you, that means I need to ask a question about thermodynamics. And I've already been messing about, I was talking about all sorts of physics, and now comes another aspect, statistical physics, okay? We don't need to know very much, but we need to introduce a thing called the chemical potential. And that's basically saying that when I write this guy down, what I'm actually doing is I'm saying that there is an energy, and it depends on how many particles I have in the fluid. Okay? And then I'm saying this is in fact the statement of that equation of state. And this is all I need. Okay? And I take one more step and I say there is a statement saying now the chemical potential is what happens if I change this number of particles. Right? How does the energy change? And then thermodynamics tells me that the P and the epsilon sitting up here is equal to n times this mu. This is called the first law of thermodynamics, kind of, which you might know, in a form that suits this problem. Okay? So instead of starting over here, which people normally do, saying that P and epsilon are the sort of primary agents, I can relegate that pressure to a derived quantity. Okay? This is what people typically don't do in relativistic simulations. Okay? And now what happens is, I take this, compare to that equation I had before, and I recast that energy conservation law into an equation that says this. Okay? That just says that the number of particles I have in that box is conserved. Right? If I have a number of particles sitting in here, when I start the simulation, that number is the same throughout. Okay? And that just says, in terms of physics, something like baryon number is conserved. Okay? So it's a fundamental law. And then, of course, you do the orthogonal. You look at what happens if I have something orthogonal to this guy. You get the usual statement that acceleration is driven by pressure gradients, as in any fluid situation. Okay? So that's a little bit of a primer, which actually points to how do I go further than just saying there's one species of particles here, and that's what I want to get to before I finish. Okay? Should get close to that now. So, two questions. First of all, how accurate in quotes, is this statement that we have a perfect fluid? Okay? So I want to try to give you a feeling for how I can answer that question. Okay? And this is kind of going one step towards hardcore fluids. Okay? But it's important that we do this because if you make contact with this diagram I had, right, with all the stuff that's in the star, which you probably couldn't see because it's a bit too bright on the screen, but anyway, all these different particles and so on. I said neutrons, protons, electrons, hyperons, blah, 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 blah. Okay? They were not one kind of particle, there were many. Okay? But now in this perfect fluid, I just had this one. So how do I get the equation of state, or whatever it is, to be just one species that gives me this perfect fluid? So let me march you through that. It's quite easy, okay, in a sense. I'll start off with saying that, okay, let's say the pressure is a function of all, say, neutrons, protons, and electrons. There's number of each, okay? Np, Nn, Ne, same, okay? And then I vary this, and then by definition, from here, if this is a definition, then the variation in the pressure just becomes variation in the mu's, okay? Like this. Okay? And then I say, okay, well look, I don't like to make life too hard for myself, so let's assume that this is charge neutral. So I've got the same number of protons as electrons, because otherwise I need to worry about electromagnetism, and if you know anything about astrophysics, you know that once you start talking about electromagnetism, your life is over. Because everything is hard. So it's Monday, we don't like that, and I'm running out of time for the first bit, so skip that. So put in charge neutrality, so we group these two together, so we've got as many electrons as protons. And then we say, okay, I don't like this, let's introduce a proton fraction. It's just saying, I've got the total number of neutrons and protons, and I work with the fraction, let's call it xp. It's just changing notation. So I write it like this. And then I say, well, okay, let's split these guys and put this xp together with this xp. So then suddenly the equation looks like this. Okay? And now I'll go in the second bracket, the difference between the sum of the proton and electron chemical potential variations minus the neutron one. Okay? So what is this guy? So this is very important for understanding these problems in general. This is a statement of how much the fluid deviates from what we call beta equilibrium. So if this is not 0, then the fluid is not in nuclear physics equilibrium. Okay, so it will want to evolve. Okay? So if this is 0, we get back to this kind of statement, which is essentially where I was. So this sequence of things you have to follow in order to get that perfect fluid. Okay? So now you can ask, is it reasonable that I push the fluid around as whatever you like? Is it reasonable to assume that it's still in equilibrium, yes or no? In most situations, no. And already you've broken this perfect fluid. Okay? Is it reasonable that it's charge neutral, that we have no electromagnetism? Well, in general, no. Because the neutron star has a magnetic field, so clearly no. And so you can march back up this estimate, this sort of argument, and see that in reality there is no way that we have a perfect fluid. Meaning pretty much any numerical simulation, pretty much anything that's done is incomplete. Tough luck. So as an example, this is where I'm going to finish. Let's say we take these relativistic equations. We are too lazy or incompetent or both, like me, to do this calculation in general relativity. We sketch it in Newtonian gravity for the purposes of the quadrupole formula, whatever you like. So you can write the perturbations of the Euler equations as some acceleration piece, gradient of pressure, variation in density in general, if you don't have this, in general, and then the gravitational potential. Now, if you want to solve this kind of problem, which we do to get some idea of what to put into the quadrupole formula for a perturbed fluid, okay, then we want to know what happens if we're not in equilibrium. Okay? What happens? Well, the minimum I need is I need some relation between the pressure and the density, P and the rho. So some perturbed equation of state. Okay? In general, this is really hard because it will involve things like if I take this fluid and I squeeze it, how rapidly does it try to get back into equilibrium on its own when I'm squeezing it? Okay? That involves all sorts of nuclear physics that we don't know. Okay? But there are two limits I can do. Okay? And it's important to explain this idea to you, because I'm going to get back to it to explain to you why when we talk about neutron star tides, what we normally calculate is probably not quite right. Okay? So there are two ways of doing it. One is to say, let's suppose that whatever nuclear physics there is, it is such that anything that happens so quickly compared to my squeezing that the matter really is in equilibrium at all times. Okay? I've already said to you that gives me the perfect fluid because I can march down that sequence of arguments. Okay? And so I know what's going to happen. Variations in pressure will, if I introduce, say, a parameter that says what is this deviation, that is 0. The background is in equilibrium, so any gradients of it is 0. So I end up just saying there is a relationship between pressure and density with some coefficient which is essentially a speed of sound. Okay? That's the usual way. Now let's suppose that's not true. There is an opposite limit, kind of the other extreme, which is way over here, that says that anything that happens is so slow compared to my squeezing that the matter here doesn't have time to do anything. Nothing happens. It keeps its identity. You know? Had some composition and so on, it keeps it as a squeeze. Then I can freeze the composition. So I introduce this XP again and say, well, actually what I'm doing is holding this fixed, crank the thing through, and I get some other expression. But now you see the pressure variation has to depend on not just this guy out here, but also what was the background, this XP without the perturbation is a background, what is the background gradient of composition? Okay? And that says I need to know more if I'm in this situation. And so this is the end, probably of everything, because it says that if we're dealing with processes that are sort of fast compared to the nuclear physics, then we need to worry about what the state of matter and so on is in the star. So let me give you an example where I'm going to get to after lunch. Neutron star tides in binary in spiral. Okay? So if Chris talked about the data analysis aspect of this Bayesian, etc., and how we're going to extract something called the love number, which sort of sounds nice and romantic, let me tell you why there would be an element of doubt. Okay? The nuclear physics timescale for reactions in a neutron star is about months to years. Okay? How long is the in spiral through the LIGO band of a neutron star binary? Any takers? Minutes, 15 minutes or so. Okay? So now let's ask, to finish, is 15 minutes shorter or longer than a month? So the matter does not have time to get back into equilibrium during the in spiral. So the calculation that we do, which is this one, is not right. The calculation we should do is this one. Problem, so I'll tell you in the afternoon, I don't know how to do that one. Tough luck. So I'm going to stop. Okay. All right. So I thought I was going to whiz through another, in a slightly different direction, this issue of how do we get from something that looks quite simple to something more realistic that looks quite messy. Okay? And I thought it would be useful to take as an example the question of how do we check how deformed a neutron star is. So I want to take a sort of textbook calculation which basically says, as I'm sure you heard from Satya because this is where we often start, what happens if a neutron star, or any star in a way, but neutron stars because they're compact, is deformed in some way, so it's got an asymmetric gravitational potential, okay? So like the Earth, for example, that we know has an asymmetries in the gravitational potential. And then in principle, if this object spins around, it will emit gravitational waves simply because of the quadrupole formula. Okay? So you probably saw the textbook calculation where you say, well, I'm just going to take this as rigid body rotation. So this is some number, the rotation rate, that is the same for all the points in the star. There's no flows or anything, it's perfectly rigid. I rotate it, I'm going to work out what is the energy. So the energy is essentially a moment of inertia tensor and then two of these omegas. So it's in 1/2 I, whatever that mysterious I is, omega squared. This hides all the matter distribution, the density distribution and so on. Okay? And the angular momentum, which is just I omega. Okay? This is rigid body dynamics. The simplest relevant problem that involves matter and is of any interest to gravitational wave physics. Okay? If you think not about binaries, but then usually we think for binaries about point particles, so it doesn't really involve any matter distribution. Okay? So we need that reduced quadrupole moment, but in this case, this I is that I bar, and then a piece here, because I'm having rigid body motion, which is constant, so when I take the time derivatives, this drop out. Okay? So it's easy. And then the easiest way to calculate this is not to worry about what happens in the inertial frame where I'm sitting over here and I'm watching the star spin over there, but to jump in a frame that goes around with the star. Okay? What I'm going to call the body frame. And then make some simplifications and assume that the neutron star does not look like this with loads of little bumps and lumps and so on. That's too hard. But to say that actually it looks a bit like this, say a rugby ball, where you have a rotation around one axis, let's call it the z-axis in the inertial frame, the 3 axes, say, in the body, and you've got 2 more axes, 1 and 2, and there is a difference in the radii along these 2 axes, so it kind of has a stretch shape, like a bar, in some shape or form. Okay? And then you can work out, if you want, that the different things you need in this moment of inertia tensor are just the differences between the moment of inertia if you rotate around the 1 or the 2 axis instead, and then some phase, basically saying what is the angle here, which is obviously now depending on time, and gives you the rotation frequency. Okay? This is a very simple textbook type calculation. We know we need time derivatives, so we need 3 time derivatives of this. That brings out 3 factors of 2 and some phi dots. Each of the phi dots is that omega rotation rate, right? So I get in the energy the number, whatever it is, these time derivatives, each of them gives me an omega, so there's 6 of them, and then this difference between the 2 moment of inertia. So the typical energy loss you get is something like this. Okay? Key lessons. As I said, if those 2 moments of inertia are the same, there is no gravitational waves, which says the body is actually symmetric around this axis. 6th power, meaning that if the star goes faster, I emit more gravitational waves, which is very intuitive, but also there's quite a high scaling, power of 6. So if I try to beat other things that don't scale so much with the frequency, this guy can become important as I spin up. So that could be the case, for example, in a star that accretes matter. So next, let's assume that I'm not allowed to stretch this arbitrarily. So let's say it's a small number, and just say, just write this as an ellipsoid with some number. Let's call it epsilon, because it's small. One day in my life, I'm going to write a paper where epsilon is a really big number. It's going to freak out everyone. It's going to say something, calculate with this parameter epsilon, and in the conclusion, in the summary, it's going to say, let epsilon be 10 to the 46. And any referee of that paper is going to reject it because it's obviously stupid calling a big number epsilon, or illegal or something like that. So anyway, take the body to be a uniform density sphere, because frankly I'm a simple person. So you get some statement that this guy is just a moment of inertia of the non-rotating body and that epsilon. Put all this together and you're done. We have this classic formula, which I think you talked about last week. A number, epsilon squared, moment of inertia, spin to the 6th power. Okay? And now what I can do is, I've got something. I know in principle how fast this object should lose energy to gravitational waves. Okay? So now I can compare with observations. Because, you know, as a theoretical physicist, your life is kind of pointless and meaningless and hopeless unless you start comparing to observations. So let me do that. Let me take the Crab pulsar, because I can and because I like it. Okay? And so for the Crab pulsar, we know from observations the spin down rate and the period, and I equate that to energy loss. I read that off from here. I work out that for 33 millisecond period and 10 to the minus 13 spin down rate, dimensionless because it's second per second. Then I work out, say, I'm going to take a neutron star as 1.4 solar masses and 10 kilometers, because all neutron stars are 1.4 solar masses and 10 kilometers. I know that. I told you that in the other lecture, that we know that for sure. Okay? So I work out what is the energy loss, the spin down in gravitational waves. Well, it's from here. It's just this number, 10 to the minus 7 times epsilon squared. So I know now, look. I know that the epsilon is 7 times 10 to the minus 4. Result. Okay? So this tells me that if the Crab pulsar has an ellipticity, this epsilon, bigger than this number, it will spin down faster than we see. Okay? And that now gives someone that builds, say, a gravitational wave interferometer and does data analysis a reason to think that maybe when you get to this number, you know you can't have a bigger definition than this, but when you get to this number, life gets interesting. Okay? unfortunately for us, in the spirit of this morning, life is not quite that simple. We know already that this is probably not the answer at all, because we know that the second derivative, the p double dot, is related to something called the breaking index, so how this system seems to evolve. And for the calculation I've done, that will be a dimensionless number that is 5 for gravitational waves with this mechanism. But observations for the Crab pulsar say it's about 2.51. Now 2.51 is not very close to 5, but it's moderately close to 3, which would be the answer for a misaligned magnetic field spin down, okay, in some simple calculation. So that basically tells you that it would be very, very surprising if all the energy of the Crab pulsar was lost to gravitational waves, because you would not be able to reconcile that with this number. Okay? So that tells you something very important, which is that this exercise gives us some number, but this number, although a limit, is an upper limit, and it doesn't tell us what the real estimate is. Where should we expect gravitational waves from the Crab? Okay? And if you go back, you don't have to go back very long, and revisit, as time travelers can, some talks given by people about gravitational waves, etc., in the past, you will see that we've gone over the last 15, 20 years from people being very optimistic, saying this is when we're going to start seeing gravitational waves, and various people doing theory, like me, saying, don't get too excited, okay? To people say, oh, well, now we have to ask things like, what is the point of carrying on? In fact, because this is recorded, and I know she will enjoy me saying this, when Maria Alessandra gives a talk later this week, one of you should just ask, what is the point of going on? And see what she says. Or you say, this is all very interesting, but when are you going to detect gravitational waves from neutron stars? It would be very interesting to hear her answer. I think I'm going to sneak in the back. So, no, I'm joking, okay, but it's a very, very serious question. And what I want to try to do now is highlight what that question entails and why, when Maria Alessandra asked me, saying, okay, look, how long am I going to have to go on? Are you going to tell me when I'm going to see this? And I'll just say, ask Emma. The point is, from the theory point of view, we really don't know. Okay? And that's what I want to try to illustrate my ignorance. So, in general, I can turn this into a limit for all the pulsars we know, right? Because I have in the pp dot diagram, I've got all the pulsars more than 2000. They have a spin period, they have a spin down rate. I just put this into this number that we've calculated with some assumption of the moment of inertia. I can be more realistic than a uniform density sphere if you want. It doesn't really make that big a difference. And so I get some idea of what is the upper limit. I can figure out that not just do I have an energy loss, I can work out the strength of the gravitational waves. It's going to be for a 10 to the minus 6 deformation at 100 Hertz in the galaxy, something like 10 to the minus 27, 28, give or take. You know that this is too small for, say, LIGO to observe this. So you know that you have to do some clever data analysis. And you probably know from last week that clever data analysis roughly, from the point of view of back of the envelope, means for something that's continuous, just keeps on going, this amplitude will improve something like the square root of the observation time. Okay? So you work out, if you want this to be 10 to the minus 21, which is a nice number, you need to gain quite a lot here, 6 orders of magnitude. You work out how long do I have to look for this thing. It's a long time. But 1 year is something like 10 to the 7 seconds. Square root does 10 to the 3. So you see that's quite a lot of years you have to wait. Okay? So this might not be big enough. But the advantage is, and why are we doing this? Well, we're doing this because, first of all, you never know. It could be that the story that I've told you is just not right. We might have missed something. So, and secondly, we have these guys. At least we know that they exist, right? And we know how fast they spin, we know how many of them are, and we know, so we can target them and look for them individually. Okay? So we can at least start putting limits, not just from some back of the envelope calculation that I've done, but from observations. Okay? And so that's why there are a sequence of papers going back to the first LIGO science runs until the 01 run. So here's the 01 data. And so it's a bit messy. You can't see it here. That's the sensitivity in some scaled units. Here's the frequency. Now each object here comes with a triangle like this, and that is essentially the spin down upper limit that I sketched already. Okay? Many of them come with blue stars, which is where the upper limit from the observations is, where you basically say, this is as sensitive as we could be for this object. Okay? Now, each of these blue stars come with a triangle, right, below it, typically. That says that, say over here, this guy is above this guy, meaning that the upper limit from the search is not yet at the level where we would expect to start seeing perhaps gravitational waves. If you saw gravitational waves for this guy here rather than here, then we would radiate more energy as gravitational waves than the rate that the star actually spins down. Now, if anyone in the room can explain to me why we would emit more gravitational waves than the observed spin down, then that would be fantastic, because that means that this whole argument falls and we can start being more optimistic. However, that's a hard thing to do, and so let's assume that we can't do that. And then some of these guys have got red dots. That means simply what was the best result from the initial LIGO era. So forget about the red dots. So in most cases, it is true that the blue star from the observation upper limit is above this theory thing. In some cases, it is not true. For example, at 30 hertz over here, there's a very faint sort of pink dot. The colors chosen by whoever made this plot for the LIGO science collaboration for the paper, that choice was appalling. Okay? That person has never used a slide like this in a talk, ever. Now I'm going to get hate mail from various people, but this figure, for purposes of using in slides, is just completely useless, right? Because you can't see any of the colors. It should be sort of bright orange and yellow and in-your-face colors, right? Blue is good, pink, not so much. I think maybe that goes for all these. So I had pink in the previous slide, clearly useless. But in the case of the crab, you see there's these guys. It's 8 of these more faint rings, circles. Those are cases where the observations actually beat this spin down limit. Okay? And that means that even though there is no detection in this diagram, and therefore people that work on searches like this now feel some sort of detection envy compared to their binary in spiral colleagues who see black holes, right? We're learning stuff. Whether the stuff we're learning is hugely important or just mildly interesting, I don't know yet, but it's a question. And so we're learning, for example, in the case of the crab pulsar, less than a fraction of a percent of the allowed energy, due to this estimate I gave you, actually goes into gravitational waves. Okay? There's 8 of them for which we're doing better than the spin down limit. The strongest constraint is with fast spin, so we're still quite far away from the spin down limit, but we know from observations that there are neutron stars that rotate sometimes very fast, like faster than a kitchen blender, okay? That have deformations smaller than 1 part in 10 to the 8. Okay? 10 kilometers, 10 to the 8, 10 to the minus 8 would be a fraction of a millimeter. Okay? Now, just think about this. Think about how stupid this sounds. Okay? It's a 10-kilometer object that has no bumps and lumps, large scale kind of thing, quadrupole. No lumps and bumps bigger than a fraction of a millimeter. What kind of precision is that? That's astonishing, right? So there's another way of turning this question of when are we going to see something to, at what point do you start feeling uncomfortable with the level of symmetry of this object? For me, 10 to the minus 8 is small, but at what point do we start getting nervous? Say, well, this number is now a little bit too small. I don't know the answer to this question, but one can start thinking about it. 10 to the minus 8 is already small. So, the question is this then. Let's turn this around and ask, okay, I'm beginning to have some feeling for how large these things can be, what observations are telling me. But what is the largest mountain, if you want to call a deformation of 10 to the minus 8 a mountain? That's maybe a semantics, but we like to be, it sounds good, right? Mountains on neutron stars. So pitiful little stretches on neutron stars doesn't sound quite so good, right? So let's call them mountains. And then you can describe your life's, work trying to climb this summit or whatever it is of 10 to the minus 8, whatever you want. So I want to sketch to you how we can estimate, or how we do estimate, what the largest mountain we can build is. Okay? And that's going to illustrate a little bit the issues that go into this. Okay? So how do we do this? Well, first of all, we plead complete ignorance and say, I have no idea. I'm going to be agnostic for the moment as to where this mountain comes from. Okay? But I'm going to give myself superhuman powers. 2 reasons. It makes me feel good, and it allows me to ignore the fact that I really don't know. Okay? So I'm going to give myself the hand of God stretching this thing. Okay? So I'm just going to take a neutron star, I'm going to stretch it. And then what I'm going to do is I'm going to assume that the neutron star has some elastic properties. So it's like a rubber or something like that. This iron lattice in the outer regions, what we call the crust, is elastic, so it has memory. It has memory, it knows what shape it would like to have, and it knows what shape it has after I stretch it. Okay? And it would like to have this other shape, but it doesn't. Okay? That means that I now have some elastic strain energy that I've given it. Okay? So how does that go, roughly? Well, I've got a total energy now, which is the energy of the unstretched object. Because I changed the shape, I changed the rotational kinetic energy, which I can express as angular momentum, J, and moment of inertia, which is not that of the sphere anymore, say, if its sphere is relaxed shape, but the stretched shape, okay? So that encodes to some sense that I've stretched it. I have some piece that says the potential energy changes because I've stretched the object. And finally, I've got this elastic strain energy, which has the shape that it has now and the shape it would like to have, an epsilon 0. Okay? This is a schematic, if you like, and just says it should have something like this. I don't know what these A and B coefficients are exactly, but anyway. And then what I can do is I say this guy, I know how, let's say this is essentially the relaxed shape plus a little bit, has an epsilon in it. And then I can ask, what is the minimum, so what is the actual shape this object is going to have? So that just says I minimize this energy at fixed angular momentum. So it rotates at some rate. So I minimize at that rotation rate, or the angular momentum, the shape. Okay? That's the shape the star will have. Okay? So that guy just gives me a formula for this epsilon. And it has a piece that is there because it rotates. Scales as rotation rate squared, which makes sense. The centrifugal force would come in at that rate. So if the star is stretched because of centrifugal force, that should be an omega squared. And it has a piece that sort of comes from this original shape that says, mate, you've stretched this material. It doesn't like to be this shape, but you've stretched it. Okay? So I've got two pieces. Now it's very easy to argue that this B coefficient, this ratio here, is a very small number. Okay? And the argument goes a bit like this, that B, if you put numbers in, is something like the compactness of the star, m over r, so this is about a 1 over a fifth, something like that. It's got the extent of the crust, delta r, over the total radius, which is about 1/10, say, kilometer on 10 kilometers, something like that. And then it has the shear speed in the crust. So the mu is the, not the chemical potential from the previous lecture, but something like the shear modulus of the material. And so this mu over rho is the velocity, so it has to be less, or velocity squared, has to be less than the speed of light, that velocity. So this is some small number. At the end of the day, this is something like 10 to the minus 4, 5, 6, 7, some small number. Okay? Typically. And then you compare to this other number, this rotational deformation, you realize that this guy is very small compared to this first term. And that basically says that if I stretch this material, typically I would have to deviate from this relaxed shape a huge amount before I start dominating the centrifugal deformation of the star, meaning that rotating neutron stars, if you could zoom in, we had an incredibly powerful telescope, we could zoom in and see what they look like, we would not be able to tell by eye that I've imposed my hand of God. They would look like rotating bodies where the centrifugal force dominates. Okay? And that's kind of an important conclusion, because that means I know roughly what the shape will be. Okay? So that's the first part. Now I need to put in a bit more physics, which makes it really difficult, which is I need to say at which point does my hand of God stretching break the material. So I don't know how much you know about material science. Like me, probably you know very little. Maybe you're experts, in which case I'm insulting you, which is good, because that makes you angry and that means you will stay awake. But let's say we know very little. So what we're going to ask is, when does the matter break? And we can start comparing to experiments in the lab, and it turns out the material scientists don't really know this very well either. This is a hard question. Okay? But typically, we can encode this epsilon I'm allowed as some sort of breaking strain that says, well, at some point it's going to break. And that means I sort of put in a parameter, let's call it breaking strain U break here, which I don't know. But then maybe someone will do a simulation or some model. And in fact, people are doing this. In particular, a guy called Chuck Horowitz at Indiana University is doing this for a living. And what he's managed to show is if you take neutron star matter in a box and you start shearing it like this, the breaking strain has a number, and it's about 0.1. 0.1 is a number. Interestingly, this number is bigger than what people expect for normal terrestrial matter. And so you come up with statements like the neutron star crust is super strong, meaning you can use Superman in your slides, which is always funny. The bottom line is the crust is super strong, but even if you put 10 to the minus 1 in here, the allowed epsilon is small, it's about 10 to the minus 6. Now remember what I said about the crab. The upper limit was 10 to the minus 4, give or take. The crust would break already at a deformation of 10 to the minus 6 away from the relaxed shape. Okay? So we should not expect gravitational waves from the crab until we get to this 10 to the minus 6, and the bottom line is LIGO might not get there. Okay? So even the biggest mountain I'm allowed to build might not be big enough. Which is why people looking for these things are now beginning to, question their own strategy. But,
excuse me?
Yeah.
I don't know that it's really related, or my brain is just making a relation. You said something before that they on the ISS they're doing tests, right? Like, and they might like be quicker than what we can do with LIGO eventually. Is this somehow related to these boxes or something? Like, I was wondering, how do you do neutron star tests on the ISS, essentially?
Okay, so the NITRA experiment is trying to map for a handful, small number of neutron stars, one target in particular, one fast spinning pulsar, is trying, but we know the mass, okay, is trying to look at the X-ray light curve and compare to theory models of the light curve essentially from X-ray emission from the surface. Okay? And that means if the models are correct, you can make an inference of the size. For these kind of things, it's very hard to see how you can do any experiment other than gravitational waves. Okay? And I think what we need to decide is, how do we go about this? And the attitude I'm taking today is that there are some questions, fundamental questions, that are very interesting, but they're also quite hard, that we need to resolve. And that's where I'm going. Okay? So you look at this, already you might think this is completely pointless. We should just stop now and have coffee. But bear with me, and I'll try to tell you why there are some really interesting questions here that will be worth kind of resolving. So this looks not too great, but let's see what I've done. First I did a back of the envelope estimate. I said there's an upper limit, which makes sense because of energy conservation, etc. It would be hard to radiate more than you're allowed, so that makes sense. Then I had asked the question, what's the largest mountain I can build? I put in the hand of God stretching this material. Then there was some material science saying that if I stretch it too much, it will break. That's the only really solid, if you excuse me, piece of information I put in, the breaking strain. So now let's see what the unknown unknowns, again in the Rumsfeld kind of speculation category, that we need to deal with. So what is this hand of God? I don't know. What is the mechanism that gives you this deformation in the first place? I don't know. Is it the case that real neutron stars reach this upper limit, or do they kind of relax this strain as they evolve? Okay, I don't know. What happens if real neutron stars reach this point? Is there a dramatic sort of shattering of this neutron star crust, or is it again more gradual? Is it like earthquakes? I don't know. So basically, all these questions point to one single thing. If we want to understand the kind of deformations that real neutron stars have, we need to be able to track and understand their evolution. Not just saying, I took it and stretched it like this, because I'm a theoretical physicist, I have godlike powers, or I can play around with things as much as I like and write some papers, but really, nature will have to do this on its own. So why does it do it? What is it that happens that stretches neutron stars? Why is the mountain there in the first place? As I said, I don't know. But it should have something to do with the evolution, the temperature, and so on. Okay. So one thing that evolution brings in is that let's have some other guy kicking a neutron star. So one way of doing this in some shape is to let the star accrete matter from a companion. Then you can imagine that the flow of matter onto the neutron star surface has some asymmetries, right? Because, say, of the star's magnetic field. So at some point, the matter starts flowing along the magnetic field lines, land at the north and south pole in some shape or form. Okay? That gives me an asymmetry. The poles are preferred over the equator, say, and therefore this star has some lumps and bumps. And in fact, this connects with a mystery, or mystery maybe sounds a bit too exciting, puzzle. Sounds like the kind of thing you do when it rains, which I guess in Scotland it does quite often, and so maybe this would be good. So when we observe neutron stars that are accreting, the fastest one we know is a guy down here. It's called 4U1608, phone number, really good. It spins at 620 hertz. But when I work out how fast neutron stars are allowed to go, I find about a kilohertz, and so there's a gap here. And so there are two ways of explaining this gap. Either there's something that stops this guy, and it could be gravitational wave emission. That's one typical assumption from our side. And then if you're an electromagnetic observer, you know that gravitational waves don't really exist, and therefore it has to be some other piece of physics. So you could just say, well, you know, the torque that you get from this matter just conspires to stop things here. So for about 20 years, there's been a discussion going as to what is what. At the moment, and this is a recent figure from Alessandro Petruno about the distribution of these stars, you see there's a peak here, kind of, highly statistically significant. Out of about 20 objects, there's no real statistics here, but let's pretend there is, which would be consistent with some mechanism that kicks in at the given spin rate. And as I told you before, this omega to the 6th power from the energy loss due to gravitational waves is a sharp rise with the frequency. So that would give you some sort of ceiling. Okay? And that could explain this kind of thing, which is why in this area people talk a little bit about gravitational waves. So what we can work out, I'm just going to actually just skip over this, you can work out, we'll look at this later, probably I'll put it up with the other things from school, work out that the fastest a star can go is over a kilohertz. It's a very simple estimate. So what I can work out is how big is this deformation supposed to be if I add angular momentum at the star's surface at some rate m dot. Okay? Relate energy and angular momentum channeled through the spin rate, and I can work out that there's a number, I'd say this needs to be twice this, doesn't matter, but there is a number, and it's a small deformation. So we have some ideas of these epsilons now. We've seen that there's an upper limit for spin down from the crab. We can beat that with LIGO searches. There was an upper limit to how much I can stretch the star. It was about 10 to the minus 6, give or take. This number, 10 to the minus 8, is smaller. So nature could do this. It could be that these systems are indeed explained by gravitational wave emission. We might never know from gravitational wave searches because these signals will be weak. We already saw what the typical number was for the other estimate. And there's quite a lot of problems trying to look for these things because this rate at which matter flows onto the star varies in time. There's some efficiency factor in between X-ray observations that tell us what the rate is, matter falling onto the star, and this torque. We don't know what it is. So this is very hard. But it could be that we're seeing indirect, again, like in the binary pulsar, some evidence of gravitational waves from these systems. So trying to model how these processes will go in these cases might be, well, I think, is a really important pursuit, even if the gravitational wave searches you would have to do would be really difficult. So here there's been quite a lot of statements about gravitational waves as well. There is a LIGO paper on signals, supposedly from an object called SCO-X1, which is the brightest of these systems in the sky in X-rays. And so I have an opinion about the idea that the brightest objects in X-rays will be the brightest objects in gravitational waves. I'm not going to tell you what my opinion is, but by just saying I have my opinion, you can figure it out for yourself. I think one needs to be a bit open-minded here. There is not a clear connection between bright-and X-rays and bright-and gravitational waves. In fact, you would like it almost to be the opposite, right? You would like something to be gravitational wave bright and completely silent, dark, or something in electromagnetism. That might be better for you in terms of losing energy. but we don't know, but he's a very exciting kind of set of sources to worry about. So I'm going to wrap up by another question. So I've talked about upper limits from spin down, radial timing. I've talked about upper limits from trying to break the star, but these are really not the questions I want to ask, right? Let's suppose you want to go into spending your time searching for gravitational waves from spinning neutron stars, right? The price could be nice, there's a lot of physics here to extract, but you really would like to know if you're going to waste your time or not, right? So if they are, let's just, for the sake of the argument, say that I can work out as a theorist that you're never ever going to see anything, okay? Ever. Then as a data analyst, you have to decide, do you want to bank on my incompetence that my statement is not reliable, you are going to see something, right? Or are you easily persuaded that, nah, it's too much work. I'm not going to go into a direction where no one's ever going to see anything. I'm going to do something else, right? Black hole binaries is a good bet, right? Which one is it going to be? Well, you could turn around and say, well, look, you've done the wrong calculation, you stupid theorist. I said, well, that happens to me quite regularly. So, although people don't call me stupid theorist so often, but maybe behind my back quite regularly. So you could say, okay, look, why don't you do a better calculation that says, instead of calculating what is the largest deformation with your supposed godlike powers, what is the smallest deformation you can have? Can you answer that? Okay, and the answer is, to some extent, yes, I can. Okay, because neutron stars have magnetic fields. And we know that the magnetic tension, say in a magnetic field that looks like this, would push matter out like that. Okay? Or magnetic field that looks like this would push the matter up like this. So if the neutron star has a magnetic field inside, which it has to, matter should have some deformation that's linked to the magnetic field strength. Okay? So can I work that out? The answer is no. But I can at least set the problem up. Okay? So for example, I can ask, okay, what is the energy budget? So the energy of the magnetic field goes something like magnetic field strength B squared, integrated over the body, over the gravitational potential. Energy, Gm squared over R. Put this in, do some back of the envelope. It says, for a typical pulsar magnetic field, 10 to the 12 Gauss, the typical epsilon is 10 to the minus 12. That's so small that you might as well not bother. Okay? But I have strongly magnetized magnetars that have got about 10 to the 14, 10 to the 15. So that can buy me, say, in the perfect world, 10 to the 6 here. So that brings me to the 10 to the minus 6, which is similar to this breaking strain I had before. So maybe it's not impossible. The problem is that these magnetars, because of the strong magnetic fields, will spin down very quickly. So maybe I'll depart from any LIGO band very soon, and so on. There are other issues. And then there's a couple of complicating things where I want to finish. First one is, as I said before, in the beginning, the other lecture, matter in the neutron star is probably in states that we know from the laboratory, but don't quite understand from neutron stars. So for example, the magnetic field is probably in the form of a superconductor, which buys you some factor, a magical factor involving the critical field for the superconductor divided by this B. That number could be something that this HC is about 10 to the 15 Gauss, so that number could be a bit big here. And so maybe it's 10 to the minus 9 with this scaling, which looks better, but it's still not detectable. So the problem here is, and this is essentially deformed neutron stars in a nutshell. Okay? It's a textbook calculation to ask, what is the gravitational wave emission from a rotating bar or a neutron star that's deformed into a bar? Okay? It's a fairly straightforward data analysis issue to ask, or that's maybe being insulting to people doing this job because it's obviously still not easy, but at least understanding the principle is quite straightforward. But then the step from this back of the envelope textbook calculation to the real physics involving how big am I allowed to make this deformation to how small could it possibly be, which I'm sketching here, is opening up a range which is quite big. Okay? And then here, unfortunately for me, these are obviously just simple numbers. I could give you better estimates of this, but they're pretty much the same. There is a big unknown, which is I don't know what the field configuration is inside the neutron star. I know that outside, far outside, they have to be essentially dipole fields because that gives me the spin down rate that tallies well with radio pulsar searches and observations, okay? But I don't know what the field looks like inside. Okay? So I wanted to finish by sketching this problem, because again, here is a research problem that people are working on trying to figure things out proper. So basically, and this is not a gravitational wave problem as such, this is a general neutron star problem. We don't know what the neutron star magnetic field looks like inside. It's a problem because we know there are neutron stars with very large magnetic fields, and in order to explain the phenomenology of these magnetars, we need to have that toroidal piece that pushes the matter up like this strong compared to the poloidal piece that pushes it out along the equator. Okay? There are no models, theory models, on the market that can give you that. All the theory models give you a weak toroidal field, a strong poloidal field. But you might turn around and say, you know, stupid theorist. Maybe. But there is a very simple reason for why we're failing. So I want to sketch that. What we do is we say the neutron star matter is in equilibrium. There's no evolution. So you just get pressure gradients, gravitational potential balanced by a Lorentz force. That's how we calculate these things. So you put in your B field, get some deformation. And then from Maxwell's equations, you just find that the curl of this combination has to vanish. Okay? So what people do is they say, well, if P is just a function of rho, then I can bring this guy together as a total gradient. Then I know from here that this piece is curl-free, and that says I can solve this with the potential. It's a standard trick. Gives us something called the Grad-Shafranov equation. So every single calculation of neutron star interior magnetic fields really assumes the matter is in equilibrium and it has this structure. It gives you a weak toroidal field, which we know from observations should be wrong. There is a trick you can cheat. You can say, suppose this is not in equilibrium in some shape or form, which is where I was in the other lecture. Then I can put in whatever magnetic field I want, because this is now does not follow this sequence, so I can break this calculation. Okay? But now I'm not in equilibrium. So what am I allowed to do? So you will find papers breaking this logic, putting in whatever they want, getting out whatever answer they want, and you have to ask, am I allowed to do this? I don't know. I would like to know.
Is there a physical explanation as to why the toroidal component would be smaller than the poloidal?
No. It just seems to be the case that if we follow this standard logic, we can't do anything other than that. That comes out. Okay? So I wanted to finish, obviously, because we're getting to that time, just by pointing out a couple of things. One, it's even worse than this, because when I do these calculations, people who do it, we find that actually, give or take, none of the models we calculate are actually stable. all these magnetic fields would start evolving and changing, sometimes dramatically. So the answer we have can't be right. There's a problem. And then the clue, I think, to the solution, which I'm going to leave with you, is maybe in that realization. If it is the case, I do a model, it gives me answers I don't like, because I can't build the kind of configurations my electromagnetic observer colleagues would like me to have. I can't do it. I'm doing something wrong. There's an extra hint that actually everything I do explodes if left to its own devices. I must be doing something wrong. Okay? So somewhere in these assumptions, I am going wrong. So maybe this answer here is more correct, although it's cheating. Right? Again, it's a hand of God kind of thing. I put in whatever I like, and therefore get out whatever I like. But I think the answer is neutron stars evolve. They cool, the field evolves because of resistivity and so on. These are complicated systems, okay? And that's the essence of this, where I wanted to go with this deformation thing, okay? If we really want to know what kind of deformation a neutron star will have for the purpose of gravitational wave searches or otherwise, we need to understand how the system evolves. And I'm sorry, but that involves loads of questions we really don't know the answer to, right? And so the point of that is I can go from a textbook calculation to hardcore questions we really don't know. So I can go from something where everything is certain to where ignorance is absolute. And this, I think, is a typical explanation, a typical example of how modeling gravitational waves from neutron stars go. Okay? Any problem you choose looks simple, the back of the envelope. It looks horrible when you put in all the physics. Right? So sometimes you just think, well, I'm just going to wait for LIGO to make a detection, and then I'm going to claim that I knew it all along. And I think at that point, let's have coffee. Okay. So, when I was thinking about what to fit into these 3 hours, I had to make some choices and cut out some things. And so, where I landed was this idea that we would go from, in general, talking about what sits on the right-hand side of the Einstein field equations, how we describe matter in kind of in general, without going into too much detail, but at different levels pointing out how what we put in impacts on things. So on these slides, which I guess we'll make available somewhere, somehow, in the fullness of time, there are some little calculations. And the idea is that they should be fairly simple, just to give you a flavor of how what goes in. Okay? And so in this last one, what I wanted to do was build on the idea of just rigid body dynamics, and then all the physics that came into the stretching the crust and breaking the crust, all that magnetic field and these things, and take one problem that has many different aspects, and remember to push the button on this laptop often enough that it doesn't freeze. Okay, there you go. And so I was thinking that a problem that's obviously very much sort of next, in a way, on the to-do list for gravitational waves is neutron star mergers. And so I was thinking I was going to walk through the physics of neutron star mergers, kind of superficially, but also digging a little bit deeper into some of the issues, and in particular, maybe telling you, from my perspective, some of the things that I think we need to do a little bit better, because I think that's maybe useful. Okay? And so I'm going to take as my starting point the same figure from Jocelyn Reed about what to expect from early entering the LIGO band, kind of through to the merger. But now I want to think about it not from the techniques kind of point of view that I had in the beginning. Now I want to think about it as a physics point of view. So way over here, when we enter the LIGO band, the two neutron stars are still far enough apart that we can pretend, for all intents and purposes, that they don't have any physical extent. Okay? As they get closer together, the tides from one of the partners is going to start stretching the other guy and vice versa. Okay? They're going to start interacting. And so at gravitational wave frequency of hundreds of hertz, whatever, this is going to become important. So there's going to leave, on top of this point particle post-Newtonian in spiral, there's going to sit a small tidal term that depends on how deformable the stars are and how big they are. Okay? In principle, then, this part of the signal should tell us maybe something about the equation of state. So I want to talk a little bit about how that is calculated, this effect is calculated today, and I want to give you some idea of stuff that we're leaving out, which I think might be important. Okay? And then eventually the stars come very close, they crash together. Clearly this is no longer pen and paper work. Now we need full nonlinear simulations. So we need to do the kind of stuff that I guess Mark talked about last week, but with matter. So what I want to talk about in that context is I want to talk about how, just in principle, how this equation of state information sits in these simulations, just to give you a flavor of why this is not trivial. You know? I'm not going to show you any movies or anything. I'm just going to show you the ideas that go in. You would have seen some of this, I think, last week, but now I'm going to focus on specific aspects. And then I'm going to show you some results that, again, give us this feeling that from neutron star mergers, we'll be able to read off some information about the equation of state. Okay? And at the end, I'm going to show you some fairly recent results on correlations between the different parameters that sit in this problem, different things we might hope to extract, and remarkably, something I don't understand, so this is being recorded, I shouldn't say things like that, but something I don't yet understand, which is that some of the features we see here are correlated with the features we see here. So the merger part seems to be correlated with the tidal part, and that, in my view, is a little bit surprising, because over here we're dealing with two separate cold neutron stars, relatively cold. Here we're dealing with one single hot object, much hotter than, so the thermal part is important. Here there are two separate neutron stars. Here this one guy is crashed together, and there's probably above it sort of the mass at which it will remain for a long time. At some point it will collapse. So it's very strange in a sort of intuitive sense to find that there is correlation between these two pieces. Okay? But I'm going to show you why we think that is the case. I don't know the explanation, but I can show you the result. Okay? So the bottom line is all of this is just pointing to more questions, and what you should take in spirit is that at some level there are lots of questions for us to answer, lots of stuff to do, and probably we need some detections to start making sense of all this. So that's the spirit. So I'm going to start with the tides. So in principle, this is a classic problem in binary interactions. What you want to know is how does one body react to the presence of the partner. And so what you can think of is that if the star sits on its own, then obviously it's just more or less a sphere. If you put in a partner, it's going to stretch it a little bit due to the tides. Okay? And so the question now is, how much does it stretch? And you can start asking, should I be worried about this? Is it going to muck up the data analysis problem? Am I going to mess up the phasing of the gravitational waves because of the tides? Answer is probably not, because if you work out how much energy it would take to shift the gravitational wave phasing by, say, 1 radian, the magical point where you go out of phase enough that you bring down the signal to noise ratio of any detection effort, you need to put in something like say 10 to the 46 ergs at 100 hertz gravitational wave frequency only shifts the signal by 1,000th of a radian. That's nothing. Okay? So that means if you really want to have an impact on the detectability of this signal, you need to put in a whopping amount of energy, and that's not really going to happen. Okay? So that's not what we're talking about. What we're talking about is a small effect that might still be detectable, maybe not from one event, but maybe from a collection of events. I suspect you saw this last week, some picture from Chris, and so on. So normally, the thing we're going to look at is something called the love number, which is a classic quantity that basically says how much is a given fluid body stretched by the presence of a companion. Okay? And so I'm going to talk about how this comes about and some of the features in this problem. Okay? Schematically, there's some numbers. The love number is called K2, say, for the quadrupole. And then what we're going to see in the quadrupole type multipole formula is some post-Newtonian term, let's call it lambda, fairly high post-Newtonian order. I think it's 5th post-Newtonian order if you calculate strictly. But then there's coefficient. This coefficient is pretty big, so it's sort of, even though it's formally at the high order, it enters into the sort of waveform at a much lower order. Okay? Because it's got this radius to the 5th bit, so it can make it fairly big. Roughly, this says how much is a star deformed in the quadrupole compared to the strength of the tidal field. So how much does a star stretch if you try to stretch it? So what we'd like to do is we'd like to detect this. We'd like to be able to put constraints on the radius. I already gave you my thinking of this. If we can do this with 5%, that would be fantastic, but the X-ray guys might get there first with NICER. So that's good news and bad news. But even if the X-ray guys get there first, it's important to do this kind of thing with gravitational waves if we can, because we will have different systematics compared to them. Okay? So this will complement what they're doing regardless of whether they get there first. So how does this calculation go? Well, in principle, it's quite easy. We need to take, again, I'll sketch this in Newtonian gravity because it's easier to see what happens. So we get some usual perturbation of an Euler type equation, acceleration, pressure perturbation, and so on. And then on the right-hand side, we have an extra piece that just says, this star, the perturbed star, lives in the gravitational potential of a companion. Okay? And then you can think of this in two ways. You can think of the companion as being over here, and how does this star, me, obviously being a star, how do I stretch because I've got a partner over here? If you sit in a frame that co-rotates with the orbit, my stretching is going to be, I'm going to bulge out towards this guy in the same direction all the time. Okay? But from your point of view, in an inertial frame, this is going to be a rotating coordinate system. Okay? So it's going to be time dependent. A better way of looking at it is to go into a frame that is not pointing towards the partner, but pointing upwards with the plane of the orbit like this. Okay? If you do that, then basically this tidal potential, expanded, has this kind of structure. You don't need to look at it. It's an expansion in spherical harmonics, where you have an amplitude piece, just 1 over the distance, time dependent, to some power. Some number W we don't need to worry about. Goes up some power law in the distance position, and then a phase phi. So the phase phi is just what is the orbit doing. D is the distance. And then there's an M here saying that the different pieces, because the sum over M is included, and there's some selection rules saying that the M and L have to add to an even number, so on. It's not really important. But the key point here is there's two contributions to this thing. One is, if this M is 0, okay, then this piece is gone. So there's no oscillatory piece to this. The only thing is the 1 over the distance. That depends on time. But that dependence in time is slow because the orbit shrinks gradually. Okay? So this is something that varies on the in-spiral timescale. Okay? So when we're far apart, it's going to be very slow. When we get close together, of course, it's not going to be slow anymore. Right? If I put m non-zero up here, then obviously this becomes a time-dependent driving. And so that means I'm pushing the fluid in a time-dependent manner, which means that the fluid can become resonant with this pushing. So if the fluid has its own ways it would like to oscillate its own waves, then there could be a resonance. Okay? So I'm going to talk about these two pieces separately, just to sketch how they come into this problem. And you're going to see that they're both important. Okay? They both encode different scalings with the stellar parameters, so we should be able to learn different things, in principle. We start with this guy, so this love number thing. So now, for all intents and purposes, if we ignore this time dependency, we ignore the in-spiral time, so we make the assumption we're far enough apart that the star goes around in this orbit, the system goes around in the same orbit for a long time without shrinking much. Okay? Then this problem becomes time. That laptop has had enough of work. There you go. I'll fire you. After this lecture, you're fired. Okay. So now this problem is time. The right-hand side is time independent. Okay. That means I can make the left-hand side time independent, so I cross out this acceleration. And what I'm looking for then is a static deformation in the star, okay, as a function of the distance. So that's called the tidal compressibility or the love number. So work it out, it's static now, looks like this. Well, the first trick is to say, well, actually, look at this, there's a gradient of the perturbed gravitational potential and a gradient of that chi driving. Put those two guys together, because they clearly like each other, they're both gravitational potentials in some shape or form. So I introduce a guy called U. And then I have an equation for this U, just write it in spherical harmonics with some index L. It's just an ordinary differential equation, so it should be supposedly be easy. And then on the right-hand side, I've got the density perturbations. But then I go back and I look at this, again expand this in spherical harmonics, and I find after massaging a bit the radial piece and the angular pieces here, that there is a relationship between the density perturbations, the pressure perturbations, and these derivatives. Now I want to pause at this for a moment, because what this equation tells me is something like this. Where it says P prime, rho prime, PL is equal to P prime rho L, what that means is that this guy here is the background d PdR, d rho dr, would be good, times the perturbation in the pressure. So that goes like d PdR times d rho dl, d rho, like this. Now, in the very first lecture this morning, I talked about barotropic equations to state perfect fluids and so on. This basically says that the perturbations are given by this kind of equation of state. So this comes out of the assumptions I make for this tidal deformability. I'm forced into this. But this morning I was talking about different timescales, etc., deal with this barotrope. I don't have a choice. Okay? And that, I think, is one of the problems with this tidal thing. And we'll come back to that in a minute. Anyway, just use this, plug it in, you get one equation, this needs to be integrated. You got this sound speed thing from this morning. There's no real mystery here, apart from now, that statement over here says that, if you recall what I talked about this morning, this fluid has to be in chemical equilibrium. Otherwise, this formulation of the problem doesn't work. Okay? So somehow, I have hardwired the description of this problem into this regime. But I think I alluded to this morning that this can't possibly be right. Okay? Because the timescales of the nuclear physics say that the reaction timescale for a fluid that's out of equilibrium, so I stretch the fluid, it should be kind of out of chemical equilibrium, but the timescale to get back into this regime could be months, and I only have 15 minutes through the in-spiral. So this can't be right. At some level, I'm cheating. Okay? This is one of the open problems for the tides. I don't know the resolution. In fact, it's even worse than that, because there is a conceptual issue that how you should do this now, I don't know. But let's forget about that for now. So what I do is I solve this differential equation, match to the exterior, read off this K. That calculation is in principle fairly easy. And then I do this for different equations of state. If I extend it to relativity, the curves look as a function of the mass. Look, the lambda, which has that K2 in it, go a little bit like this. And the key idea that you would have seen in probably the data analysis discussion is I should be able to, in the perfect world, read off the difference between these guys for a star of the same mass from the observations. Right? Doing that, I will know which equation of state I've got, I will know what the radius of the star is, and I'm in business. Okay? So this is the logic. Now, maybe the problem could be that we're dealing with, first of all, the need to extract many signals, combine them to get this imprint. The second one is that maybe, if you look at the analysis that have been done so far, maybe they picked equation of state like, say, suppose I set myself the task of distinguishing this guy from this guy. That might look pretty easy, right, because they're far apart. But maybe if the real equation of state you have to compare these two, it's not so easy. Right? So it's still not clear, I think, whether we're being realistic when we're estimating to what extent this can be done. Okay? This is a problem, I think, it's been going for a few years. There's quite a lot of issues. I'm going to come back to one more in a minute that I think people are now really worried about. But there's the essence here is this problem has more physics involved than we might pretend. And also, if you go back, of course it is the case that I ignored the time dependence here. So as the binary shrinks, at some point this is just not going to be valid anymore. Right? So at some point from entering the LIGO band before merger, this is going to break. Okay? And then you'd have to ask, okay, so how does the time dependence go? And this becomes much messier. That was point one. Point two, let's look at this other part where we've got time dependence here. And let's just simply ask, what happens? Well, in principle, you can recast this now. I need to worry about the time dependence over here. And you can recast this as a problem where the fluid motion could become resonant with the orbit. So the orbital tide drives the fluid. If the fluid is like, you shake a bridge, if the bridge likes to be shaken, it could start wobbling with the wind or whatever it is, like the wobbly bridge in London that was a great success for a while, if you wanted to be seasick. This is the same kind of thing. If the star likes to be shaken, so if you shake it at the right kind of frequencies, you could get a resonance. So that means we need to start asking, okay, so what is the fluid dynamics? How does it react? So let me sketch, because I can, the simplest mode of oscillation of a star. So just assume the star is a uniform density ball or something like this. It's worth doing because it highlights something that actually will turn out to be important. Okay? So how that goes is you can set up and just assume that you again solve the perturbed fluid equations. Now there's no tidal driving, forget about it. if the fluid is strictly incompressible, the first thing you learn is that you have to have vanishing divergence that comes from the mass conservation. And then everything else basically follows from Laplace's equation. So this is a very simple example because all I need to solve for the velocity field, pressure perturbations, gravitational potentials, everything satisfies Laplace's equation. Laplace is happy because he now governs the whole universe, everything. That means that if I expand in spherical harmonics, I know exactly what happens for everything. Don't need to do anything at all, it just ends up being an algebraic equation. So that is really easy. Okay? I need to relate these coefficients. I call them A for the velocity field, the stream function, B for the gravitational potential, and C for the pressure. I need to relate those. So I know how to do that because, first of all, the fluid has a surface. So if you're sitting on the surface of the star, basically, what's the definition of the surface? Well, that's when the matter ends, right? So the pressure vanishes. And so if you want to ride along with the surface, you ride along with the vanishing pressure. Okay? Secondly, the gravitational potential, well, it has some dependency on the matter inside. At the surface, it has to match to whatever happens outside, or it doesn't care about what's going on anymore. It's just a point distribution at the center, essentially. So I'm going to cheat because it's after lunch, but if you're not asleep yet, you will be soon. All right, so I'm going to cheat. You won't notice, apart from I just told you, which I guess was a bad strategy. But okay. So I'm going to cheat and I'm going to ignore the gravitational potential. It's something we call the Cowling approximation, because when you're cheating, it sounds much better to say this is the whatever approximation. Right? And then blame someone else. So now I'm blaming a guy called Thomas Cowling who worked on just oscillations of stars like the sun a long time ago. So he suggested this approximation, and since then we've all been abusing it, something rotten. The problem I'm looking at right now is actually not valid. In school last week in India, I had the students calculated with and without this approximation in one of their tutorials to see how accurate it is. It's about 20 to 30%. That's not really much of an approximation, it's a cheat. Okay? I don't care. So then what I'll do is I'll just say, okay, I'll ride along with the fluid surface, gives me some condition, gives me an equation that relates this C and the A. Well, I had A, B, and C, alphabetical, very good. I've thrown away the B, so now I need the relationship between A and C. Have one from the equation, I have a new one here. That means I can solve, because frankly, I'm a really good mathematician, okay? I've got a relationship between A and C, and another one, I can eliminate this and get a frequency. Even I can do this at my advanced stage. Imagine that. Okay? So I get a statement straight up. The frequency of this goes like this. Okay? Why did I bother talking about this? Well, I bothered talking about this because actually this teaches us something really important. Okay? When you look at the fluid dynamics of finite bodies or stars, the stars have a huge variety of different ways it can oscillate and vibrate, different waves in the star. They tend to depend on what physics you put in. Okay? In this case, I put in no physics, other than that the star is a ball. Constant density means I can't have any sound waves or anything like that. It's just a ball. So it has a surface. So this thing I've written down, the frequency of this guy is called the fundamental F mode. Amusingly, perhaps, or maybe not so amusingly, it was first calculated by Lord Kelvin a long time ago, before spherical harmonics were invented. So you would make quite heavy use of spherical harmonics to do this thing. Some years ago, we decided as an undergraduate student project, we're going to ask the students to work this out. And so we gave them as literature Lord Kelvin's paper. And I'm afraid to say that our students, our undergraduates, they didn't know spherical harmonics very well. So we had this idea they would learn to appreciate the beauty of special functions. It's a nice sentence, right? You're thinking, Christ, this guy is nuts. Okay, anyway, that was the idea. But then we gave them Kelvin's paper, and he didn't use spherical harmonics. It was completely pointless. It was self-defeating purpose. They all came back and said, what is going on? And so this project didn't last very long. Anyway, so what I've done is I've done a thing that cheats a lot, but we learned something really interesting, believe it or not. We learned that the frequency of this guy goes like the omega on its own, goes like the square root of the density. Okay? And it also scales with the spherical harmonics index. That's relevant for another reason, but I'm not going to talk about that. So you could ask, okay, real stars are not constant density, whatever spheres. They're more complicated. I've tried to convince you that stars, fluids are more complicated, and then here I am making reductionist assumptions that lead to something like that, and then I'm going to try to convince you this is relevant. Am I not contradicting myself? Yes, of course. But the question now is, what happens if I take realistic equations of state, some proper density pressure relation, whatever, and do the same calculation? You find that these kinds of scalings are extremely robust. Okay, so here is an example from a long time ago, when I was much younger than today, of the frequency again, this guy, but for a range of different equations of state, most of them ruled out or outdated or whatnot, it doesn't really matter. You can take another set, they're going to get the same result. And here is the scaling. Density, square root, frequency, this scaling here is this scaling here. So that says we can do these simple calculations, and this can be made much bigger, put more physics in. Depending on what the physics in, what you're looking for is some scaling relation. Now you're definitely fired. Okay? And then what you're hoping to do, in the fine tradition of something called astroseismology, which started off for the sun, trying to look at the vibrations of the sun, figure out what the sun is made out look like inside. Okay? So here's the same idea. If I could read off a frequency from, say, gravitational waves or something, I would know what the average density was. Right? Now that's not enough to read off mass and radius on its own, individually, but maybe if I had two of these kinds of things, I could get enough information to constrain both. That's the idea. Okay? And this is a much bigger area than I've got time to talk about now. Suffice it to say that actually we've had a goal for real data at doing this because we've seen quasi-periodic oscillations in the tails of strongly magnetized stars that flare. So they go out into outbursts with very powerful flares in X-rays, and you can look at the tails of these wibble wobbles, and you can map those onto essentially oscillations of the outer layer of the star. So you can put this into practice.
How does the rotation of the star affecting modes?
That's a fantastically good question. And the answer is essentially in three ways. One is you get the deformation of the star, obviously changing the shape, okay? Meaning it's not a sphere anymore, meaning that all these spherical harmonics couple and it becomes messy. The other one is, in general, what I've calculated here, you'll note there's a square, right? Take the square root, you get two sines. If you think about what these guys do, one of these waves is going to move this way on the star, the other one is going to go that way. Now imagine the star rotating. Okay? Then the one that goes this way is going to be dragged forwards a little bit compared to you. The one that starts out backwards is going to be dragged forwards as well. Now, if you keep on going, spin the star up, the one that goes backwards, dragged forwards, could get to the point where, according to you, it starts going forwards as well. Whereas according to me, on the star, it's still going backwards. And that's the condition for essentially this mode becoming driven unstable by gravitational wave emission. something called the Chandrasekhar-Friedman-Schutz instability. That's a big problem area of relevance to gravitational waves, which I'm not going to talk about, even though that's probably what I spend most of my time actually trying to figure out. I'm not going to talk about it because I decided to try to simplify the story to something that kind of has a narrative that goes to the end, if you see what I mean. Otherwise, we'd now start talking about when the instability becomes active, how it works, what tries to kill it. And that's a very complex kind of story.
And for typical rotation rates, is this treatment?
So what you can do, again, a very good question, you could do this calculation, but for rotating stars, and ask, is this a relation still robust?
Yes.
And the answer is yes. You can show that there are still robust scaling relations, even if the star is rotating, but now you need to think a little bit more as to how you put in the rotation in the scaling. Okay? So that has been done. So yes. Which is good, right? Otherwise this would be, given that we know neutron stars rotate, it would be kind of pointless. Okay? Okay, so that's lesson number 1. But remember, I wasn't really talking about individual stars, I was talking about binaries. So how does this guy come into play? Well, let's just look at what the frequency would be. There's a frequency here. We can read off here, see that this typical frequency of this mode is something like 2 kilohertz or something like that. Okay? But if you know anything about binaries, you know that the merger happens before this. So the story I've told you means that this mode is completely irrelevant for all intents and purposes. Tough luck. But I needed to fill up some minutes. Actually, it's not irrelevant. What was shown by Tanja Hinderer and colleagues fairly recently is that even though this F mode does not become resonant, it starts impacting on the waveform because this resonance with this mode is quite broad. Okay? So that means you don't quite hit this thing where in resonances in general you have a singularity, if you like. Right? You don't get to that point, but you get to the point where you get the lead up, where you start shaking a little bit with this, okay? Even though you're not there. So here's an example. This is the quadrupole love number I talked about. This dashed line is what you would get as a function of separation if you ignored any time dependency in this tie. Right? And here is what you actually get up to basically the end of the in-spiral if you account for this link to the fluid dynamics. Okay? So you learn from this that way over here, early on in the in-spiral, yes, it is indeed, we're far away from this resonance, it's not important, but at the end, the strongest part of the signal, you have quite a large fraction of this tidal response related to this dynamical piece. Okay? And so that, I think, tells us something important. It tells us that, you know, the dynamical part of this in-spiral, the tide, is obviously in play. It means that there might be an imprint here that we don't really think about too much, which is the scaling of the mode I just sketched, that depends on average density, is hidden somewhere in here. There's some other scaling with the fluid that sits in this love number, okay? And what we need to extract is a combination of these. So that means two things, kind of contradictory maybe. First, it means if I could extract both these pieces, then I've got two pieces of information. I can now constrain physics more. So that's good. What's bad, of course, is, see, the laptop had enough, right? Before lunch, he was happy to work. After lunch, needs a nap. So the flip side is I need to distinguish the two to extract any information reliably, and that could be difficult. And then there's another part to this tide story, which is worth mentioning because I think it's something people are really worried about. there are many other oscillations of stars, neutron stars, that could be relevant, that would become resonant in principle, but we don't think they're very relevant, even though they have lower frequencies and so on, those modes, because they don't couple strongly to the tide. Okay? So the idea is that the system just spirals through these resonances without much effect. And then recently, fairly recently, a couple of years ago, the MIT group did some work on instabilities of these couplings. And they found that there was a surprisingly strong instability associated with the coupling between the tide, on the one hand, the sound waves of the stars, something we call P modes, pressure modes, and gravity modes that got something to do with the composition of the material. And this is a very puzzling effect. That's called the PG instability. It's very puzzling because, first of all, it's a non-resonant mechanism, which I confess I don't understand how it works. So it's good to have that recorded for posterity. Anderson does not know, as if that wasn't clear already. But it's claimed to have a massive effect on the wave phasing, potentially to the point of destroying any templates you might use to search for these signals. And so, psychologically, at a point where we haven't seen any neutron star binary mergers, any statement like, and here is why you will never see it with the technology you're using, is painful. Right? Even shocked the laptop into submission. Okay? The moment we see a neutron star binary in LIGO, using the templates that without this instability mechanism and this effect, we will know if this story is just irrelevant to us or not. Right? Until we see anything using the search methods we have, there will always be a doubt. Right? You see how this kind of statement, even though most people don't understand how this mechanism would work, trust me, for some reason, there's this kind of circular argument. Everyone that kind of knows something about this, outside the MIT group, keep on saying, oh, go and ask X, because X will explain it to you. And X will say, why don't you go back and talk to Y, because Y will explain. It goes circular like this. Nobody wants to take the blame for this. You know, nobody really understands it. The papers are, dare I say it, incomprehensible, at least to me. And so this is the big issue. The point I wanted to make here about the tides is that there are aspects that we know and understand, which the tidal compressibility, the deformability, the love number, but there's issues to do with the time dependence shows up, and there are issues to do with other things that could show up to corrupt this story. Okay? So this is unfinished business. Okay? Of course, observations would start helping us figure this out. Okay? So in the last 15 minutes, I want to talk about the merger itself. So I want to do two things. They're fairly simplistic. I want to start by just saying, well, I started talking about fluids this morning. Remember, I talked about flow lines, full velocity of the fluid, tangent to this kind of flow line. And now I want to ask, what happens if I do this problem? I want to work out the nonlinear dynamics of these problems. Okay? So now I want to put the Einstein equations on the computer. You saw this, I think, last week. Yes? Some shape or form. With the fluid. So my focus is not going to be how do I solve for the space-time nonlinear dynamics and so on. I'm not interested in that. Well, I am, but not for the purposes of now. I want to talk about what happens if I put a fluid into this problem. Okay? Remember, the fluid only knows what happens along its own world lines. Each fluid element moves along some trajectory. Doesn't know anything about space and time. It just knows there are this many particles in this little box with this composition, etc. It moves like this. Okay? How do I do this in numerical relativity? Well, starting point is exactly the same as without matter. I need to put time back into Einstein's equations. Einstein's equations, of course, the beauty is that they don't have time as a separate thing. Time is subjective, right? You choose. But now I've got the fluid. I need to have some time. The computer needs some time. Coordinate, otherwise it can't march forwards. Doesn't know what to do. Okay? So what I do is I slice up space-time like people do with some new coordinate that I'm going to call t. So this is, again, a bit of psychology. We know that if I put coordinate called t, then that's time. Right? I should call it something else, like x. Again, it's quite exciting to write a paper where you call the time coordinate x and the space coordinate t, and see how the whole world collapses. Everyone gets angry with you because they get confused. But you could do it. Anyway, and then you work out simply, you put this slicing in. The time coordinate, now everything is going to march in the direction of the normal to this surface, which of course, if t is some level surface, this is just the gradient of this surface, just like in 3D and maps and so on. And then you read off that the time coordinate is along this normal, but each coordinate can drift in the surface. So I've got this alpha, how much you march forward, and beta, how much you drift. They call the lapse and shift. You might have seen this probably last week. But I'm not really that interested in tracking what happens in space and time. I want to know what happens to the fluid. So the key point is, how is the velocity of the fluid element, this guy, full velocity of this guy, related to this m? So what you do is you say, well, a piece is along here, and a piece drifts relative to it. Okay? And then you just work out, this guy is normalized, as all four velocities are, say to -1 if I'm working in c equals to 1. This guy, n, I'm going to treat like a four velocity. It's also normalized. So I can work out that the relationship here has this coefficient w, which is just the Lorentz factor. So it's the Lorentz, time dilation factor, whatever you like. Okay? So now I have the translation between the picture this morning and this 3+1 picture. Okay? This is all I need from taking the equations I wrote down this morning and translating them into this numerical relativity language. Okay? So I'm going to do that. Here's the equation I sketched this morning for baryon number conservation, for example. I just put in this thing I know for this u in terms of the n and the v. Okay? I crank the handle a couple of turns to get it into this shape. And now if you know any fluid dynamics at all, you recognize that this is just a usual, so this is time derivative, this is space derivative, drop this beta, this is just a normal continuity equation. Okay? So this exercise for fluids essentially means that you're going from space-time with covariant, contravariant objects, splitting it up into something that suddenly looks like Newtonian physics again. Right? So it's like, seems like a backwards movement where we take something that's nice and coordinate independent, put these coordinates back in, and suddenly we've got Newtonian physics back. Of course, it's not quite that like that, but it feels a little bit like that. Okay? And it's got things like this n with a hat is really the fluid density measured according to an observer with length contraction and things like that. Let's not worry about it. The key issue I wanted to talk about is this. When I do this, I have a stress energy tensor in this 3+1 picture that has something where I expand along this n, the normal vector. I've got some fluxes orthogonal to it and some stresses. Okay? This is a very generic kind of thing. But the fluid itself doesn't know anything about this. This n thing, the foliation, was my choice. Right? The matter doesn't know what I'm choosing. The matter knows I've got a pressure, an energy, and I move like this from this morning. Okay?
But how do we know how many energies in the form of gravitational waves and in electromagnetic waves?
That's a good question. So in this case, the gravitational waves are all hidden, right? Electromagnetism would have to enter in here. Okay, gravitational waves will sit in the metric perturbation, so they would not show up in this epsilon. But yes, an electromagnetic field would have to be added to this. I'm going to come to that in a second. Okay? What I wanted to drive home is the following point. Okay, this object. Okay, but the fluid physics sits here. Okay, that means that whenever I work out things like the energy, which is something like this, from the evolution, I need to, in order to impose the matter physics, I need to translate back here to the E's and the P's and so on. Right? And then I need to translate back to perceive the evolution. Okay? Now this is a fairly simple procedure for this kind of equation of state. Right? But if I follow your question and I say, what happens if I put in an electromagnetic field over here? Then this translation from evolved variable to the primitive, the physics variables, if you like, gets a real mess. At each time here, you've got to do some sort of root search to find what is the pressure and energy and so on that fits this for some given magnetic field. So this is the bottleneck, in a way, for making numerical relativity simulations with matter more realistic. Okay? And it's quite a severe thing. If you look at what people are doing, this is a point where we have to be creative, and I think this is actually holding us back a little bit. Okay? So the point of doing this is, yes, he was kind of technical, but the point is, in numerical relativity, what ends up happening is you end up with equations that look more like intuitive Newtonian-like equations, which is good, because we probably have better intuition, but there is a penalty because you need to always translate to what the nuclear physics says, and that's a difficult thing to do. Okay? So that's pretty much it. So what happens? Now let's have a look at some results to round this off. So the merger is really complicated. Two neutron stars come crashing together, fairly high velocities. There's shocks, there's heating, there's stirring of the magnetic field, whatever you like. But we're learning from simulations that there are some robust features, which is good if you're looking for these signals. So here's an example from simulations by Andy Balswein a few years ago, and other people are doing similar things. Typical frequency distribution looks something like this, a spectrum which has a very clear peak at 2 and something kilohertz, meaning it will be difficult to see with LIGO, maybe next generation or something like that, depending on the distance. But this feature here is always robust. There are other bits, like this little bump, little thing, but this is always robust. Every single simulation agrees with this. Now, what is this peak? Well, it turns out this peak is, we think, nothing but the fundamental mode of oscillation of this remnant. Stars come together, now they're hot, etc. But this guy has all the scalings that I just showed you for that F mode. Okay? So in principle, if we understand how much mass is involved in the sort of remnant, we can read off the physics associated with this. Okay? And this is a very robust feature. So that's incredibly useful, given that this is a very, very messy piece of physics. Okay? Here's, again from Andy Balswein, a set of snapshots from this kind of evolution. This is just to give you the idea as to why it makes sense that there's this robust feature. Stars start coming together a little bit later, and then here you can see when they start coming together, this guy rotates. Okay, clearly this starts looking like a rotating bar. Right? There's still a sort of deformation here, deformation. So this connects with the previous lecture where I talked about stretch stars. It connects with that F mode, which is essentially a mode that stretches a star like this and then oscillates. Okay? So there's no surprise, intuitively, that you see these robust features. Kind of had to happen. Right? Two stars come together, start touching, there is some rotation in this system, it's going to look like this. here's the surprise where I'm going to finish. This is from Sebastiano Bernuzzi and Tim Dietrich. The one I want to focus on is here. This is that frequency again of that peak I just showed you. People have got different notation for it, but this is the same guy. Scale to the mass. Here is something called kappa 2t. Okay. The first thing we want to note is that there's a curve here, different mass ratios of the stars. It's a fairly tight clustering along this curve. Okay. So there seems to be a correlation between this object, this frequency, the peak in the spectrum, and this guy. So what is this guy? This guy is a weighted average of the two love numbers. Right? So this connects the merger with the tidal deformability. I don't quite understand why this is true. Right? It's not that I'm simple or anything. Or maybe I'm simple. But it's not obvious why, as I said, the tidal deformation of two cold stars with the cold matter equation of state, right, should be linked to the wibble wobble of the merger remnant with the hot equation of state. Right? Why is that correlation so strong? I don't know the answer. I think we need to think about it. The key point, I think, is correlations like this, or other things, there are other correlations with the same parameter and other quantities, but correlations like this are really very, very important for assisting detection efforts and parameter extraction efforts. Okay? The problem is, this is nice, but if we put in more physics, these things can change. So it's never clear how robust a feature like this is for changes in, adding more stuff. Ultimately, we need to add as much physics as we can muster in order to understand how robust these things are. And that's a pretty challenging program, okay? And I think at that point, I should stop. The bottom line is there's a lot of questions, a lot of things we don't know. Yes, we've come a long way. Some of these things we need detections to sort of understand. In other cases, we just need to be able to get a little bit better at what we do. Much of it is a dialogue between standard mainstream astronomy, nuclear physics, and gravity. Okay? I find that very exciting. That's why I do it. So at that point, I'm done.